Not yet? Not yet? Okay, 1 second. Okay, say the host disable participant screen sharing. So the host, I think the hosting person is, you allow me to.
Sir, we will currently make you the co-host of the session so that you will be able to share the screen.
Okay. Okay.
So please see whether it's activated now.
Can you see my screen?
Not yet.
Can you see my screen? Not yet? Yeah, can you see my screen?
No, not yet.
Still not. Only you. We see you only.
Oh, okay. 1 second. Can you see it?
No,
No.
sir. Sir,
Oh.
is the option there, right, sir? It's activated, right? Your share screen.
Yeah, it says share screen. Yeah, it's in green. But here, set advanced sharing option, or one participant can share at a time multiple participants. I'm not sure, I guess it's advanced or what one? Let me see advanced.
1 second. Sir, can you try once more?
Yeah, I will try. Okay, I have two options. Select one participant can share at a time. The second one is multiple participants can share simultaneously. Which one shall I select?
Maybe the second one.
Second one.
Multiple participant.
Yeah. Yes.
Okay, cool. Yeah, already selected. Let me see, you can see my screen. Can you see it?
Not yet, sir. Sir, let's do like this. First, we will finish off this inaugural session, and then we will see what is happening. How can we correct that, and maybe we will proceed. Is that fine, sir? Presently, like you will be sharing the screen only during your keynote session, right, sir?
Yeah.
Can we do so?
Sure. Yeah.
Thank you, sir. Sir, Aksar, is that okay, sir?
Yeah.
That's okay. That's okay. That may be better.
Yeah. Thank you, sir.
Okay, now I can see. Yeah, good. Can you see my presentation?
Yes, sir.
It's
That's
coming.
cool. Finally.
Thank you.
Good morning, all. Can I have a sound
Morning.
check? Am I audible?
Yeah, you are audible.
Yes.
Dr. Vidyachandran, shall we start?
Okay.
Yes, sir. Yes.
Can I start my presentation? Can I start my presentation?
So we have an inaugural session before the talk, and
Okay.
we will be hosting that after 9:30. At 9:30, the talk will be starting.
Okay, so today we'll start the keynote speech.
Yeah, at 9:30.
Okay.
Yes, sir.
Success is not the key to happiness. Happiness is the key to success. If you love what you're doing, you will be successful. Very good morning to everyone present here. After the successful conduct of ICCME 2015 and ICCME 2017, we, the SCMS School of Engineering and Technology, is hosting ICCME 2021, aims at bringing all the engineers, scientists, academicians, and students to a common platform. Ladies and gentlemen, myself Sanju AC, Assistant Professor in the Department of Mechanical Engineering, SCMS School of Engineering and Technology. On behalf of SCMS School of Engineering and Technology, I take this privilege to warmly welcome all our delegates on the first day of the International Conference on Computing in Mechanical Engineering. From the words of Mother Teresa, prayer is not asking. Prayer is putting oneself in the hands of God. I invite the prayer group for the same.
हमको मन की शक्ति देना, हमको मन की शक्ति देना, मन विजय करे, दूसरों की जय से पहले खुद को जय करे। हमको मन की शक्ति देना, भेद भाव अपने दिल से साफ कर सके, दूसरों से भूल हो तो माफ कर सके, झूठ से बचे रहे, सच कदम भरे, दूसरों की जय से पहले खुद को जय करे। हमको मन की शक्ति देना, मुश्किलें पड़े तो हम पे इतना कर्म कर, साफ दे तो धर्म का, चले तो धर्म कर, खुद पे हो सला रहे, बदी से ना डरे, दूसरों की जय से पहले खुद को जय करे। हमको मन की शक्ति देना।
Thank you, Tushar. To welcome is to show honor. To welcome is to establish integrity. I invite Dr. Praveen Sal CJ, Principal, SCMS School of Engineering and Technology, to deliver the welcome address. Sir, please.
Thank you, Sanju. And good morning to one and all. So we are in the online inaugural session of the 3-day All India Council for Technical Education sponsored 3rd International Conference on Computing in Mechanical Engineering, ICCME 21, organized by the Department of Mechanical Engineering, SCMS School of Engineering and Technology. I would like to take a couple of minutes to begin with in introducing our institute. SCMS School of Engineering and Technology is promoted by the ICCME group and was established in the year 2001. We are among the first 10 colleges to be set up in the Kerala state, India, under the private self-financing scheme. Then right from day one, we concentrated on providing quality education in a highly disciplined environment. And this has paid rich dividends over the past years. We got accredited by the National Assessment and Accreditation Council, NAC, and the National Board of Accreditation, NBA. And it is evident from the flying colors attained by our students in academics, placements, as well as extracurricular and co-curricular activities. As we all know, with a rapidly changing technological scenario in the context of ever-increasing global connectivity, as well as competitiveness in modern times, the role of technical education in economic development has become very significant and more challenging. Technical institutions provide the technical manpower needed to meet the requirements of any nation. And in these institutions, the most important component of the information knowledge transition is facilitated by the teachers, the intellectual resource of any academic institution. And to be a proficient teacher in any field, one should have a sound knowledge and associated skills of the subject and its application with the prevailing practice in real life. Truly speaking, that knowledge of practice, that is its real application, helps one to be a subject expert and a competent teacher. Such situations are ensured in several other professions, such as the medical profession, the legal profession, etc., where the teachers are simultaneously the practitioners as well. In the domain of technical education, this condition is very scantily catered, or it is totally missing. So some ways and means need to be evolved to provide such exposure to technical teachers. There are two very important challenges for the present day technical teachers. First one, we must keep ourselves abreast with the latest developments in our own fields or the cutting edge technologies to be at par with the world class. And the second one, to develop the competence to visualize the indigenous needs creatively and to find appropriate solutions which are useful and user-friendly. We as teachers are responsible for shaping the career of the students and are expected to be an expert and should be skilled with latest trends and technologies. To develop such competence and culture of creative innovation, one needs proper training and practice. Conferences have been considered as a perfect way to stay up to date with industry developments in relevant fields. Conferences are often the first airing of cutting-edge ideas, concepts, and developments. And if one wants to be at the vanguard of innovation, conferences are really helpful. So it is an all-round learning experience compared to sitting at our desk, skimming a book or industry magazine. We'll get to see and hear presentations, questions and answers, discussions, and all these will enable us to guide our students on their journeys of inquiry and discovery. Now, this international conference is on computing in mechanical engineering. So being a mechanical engineer, I can say with a high level of confidence that we use computers more extensively than any other physical scientist. Computers are used to help in the design process. They control manufacturing equipment and robots, and are used extensively in the fields of fluid mechanics, solid mechanics, and heat transfer. As many fields of mechanical engineering are so mathematically challenging, computers are extremely helpful and are used constantly. We are not the engineers who build the computers, we just use them. But if you like to use computers, there is no better field than mechanical engineering. The power of modern computers makes it possible for mechanical engineers, for example, to study the proposed aircraft and car body designs before companies go for the expense of building physical models. Using computer simulations, engineers can visualize the fluid flow and temperatures in areas that are experimentally inaccessible. For example, the inside of a car engine. Now, we all know that they are used in research to extend investigation beyond the limits of experimental setup. It is often much quicker to run a computer experiment than a physical one. When computer investigation is combined with careful experiments and sound theory, the productivity of computer research can be tremendous. ICCME 21 aims to brings together leading academicians, scientists, researchers, and research scholars to exchange and share their experiences and research results on all aspects of computing in mechanical engineering. It also provides a premier interdisciplinary platform for researchers, practitioners, and educators to present and discuss the most recent innovations, trends, and concerns, as well as practical challenges encountered and solutions adopted in the fields of computing in mechanical engineering. Now, let me propel on to my duty of welcoming this August gathering in this online session. First, I would like to welcome and thank the chief guest of the day, Dr. Gerardo Carvajal, Associate Professor in the Mechanical Engineering Department at Florida Polytechnic University, USA, for taking his precious time out and gracing the occasion with his presence online. Welcome, Mr. Carvajal, to ICCME 21.
Thank you very much for the introduction.
Now,
first of all,
thank you, sir. Thank you. I also thank and welcome all the keynote speakers and resource persons for accepting our invitation and taking out their valuable time to share their knowledge and experience with us. Then thanks to All India Council for Technical Education and SCMS management for their support, guidance, and encouragement for conducting this international conference. Then my cordial welcome to Dr. Anitha G. Pillai, Dean Academics of SSCT, to this session. My sincere appreciation to all the participants for participating in this conference, despite the unusual difficulties of the moment due to the COVID-19 pandemic. I would also like to welcome and appreciate Dr. Rag RL, Head of the Department Mechanical Engineering, then Dr. Vidya Chandran, Organizing Chair of ICCME 21, and the entire team for all the time and effort that each one of you put into this international conference. Thank you all and have a nice time ahead.
Thank you, sir, for that enlightening thought for this day. It is my pleasure now to invite Dr. Rag RL, convener ICCME 2021, professor and head of the Department of Mechanical Engineering, SCMS School of Engineering and Technology, for about the conference addressing. Over to you, sir.
Thank you, Sanjay sir. Respected and our beloved principal, Dr. Praveen Sal sir, chief guest of our program, Professor Dr. Gerardo, Professor Alam Mahabub, Dean Academics, Professor Dr. Anitha G. Pillai, Organizing Chair of ICCME 21, Dr. Vidya Chandran, dignitaries from the management and leaders of different sessions, and dear participants. Since the inception, the computers initially solved simple problems of the humanity. When the generations of the computers are changing, the problem-solving ability is also increasing. There are many processes which are too fast or too slow, and the minute details cannot be traced during the experiments, which is a challenge to understand the real problem. By the growth of computational techniques, we are able to find out what exactly happens and to understand the real physics of the problem. During early 90s, if the time required for a computer to solve a computational program was 7 days, now it is a matter of a couple of hours with much more accuracy. Computational skills, when used effectively with scientific experiments and sound theoretical knowledge, can tremendously increase research output. Processes such as fluid flow, heat transfer, solidification and melting, combustion in the IC engines, and many other complex and fast physical phenomena can be visualized, and very minute aspect of these processes can be better comprehended through computational techniques. It's my privilege to share the highlights of ICCME 21, ICCME 21 focuses on the applications of computation and simulation techniques in mechanical engineering and related fields. With the sponsorship of AICTE, the Department of Mechanical Engineering is organizing the third edition of ICCME after the grand success of the previous two editions, ICCME 15 and ICCME 17. The program holds an added advantage of hands-on training session on multiphysics engineering simulation software Omnis 5.1 for the conference participants offered by Cadence Numeka, Belgium. The conference also includes plenary talks, keynote sessions, technical paper presentations, and panel discussions. Professor Dr. Gerardo from Florida University, USA, Professor Dr. Dean Vushnish from Fry University, Belgium, Professor Dr. B.V. Reddy from Ontario University, Canada, Professor Dr. Alam Muhammad Mahbub from Harbin Institute of Technology, China, Professor Dr. Arul Prakash from IIT Madras, Professor Dr. C.B. Shobhan, Professor from NIT Calicut and Visiting Professor of Georgia Institute of Technology, USA, and Dr. Shekhar from Anna University are sharing their research experiences during the keynote sessions. We are happy to inform that around 400 participants are attending the international conference and we received 140 publications. 93 publications were shortlisted for presentation. After the received manuscripts, around 53 are from Kerala and all others from other states and abroad. 17 sessions are arranged for paper presentation. Based on the quality of the selected works, the publications will be made either in AIP or Springer, who are our publishing partners. The wholehearted support from the management of SCMS Group of Institutions and the authorities of SCMS School of Engineering and Technology made this program into a reality. During this pandemic, also, we are able to share our thoughts and research works under ICCME 21. I hope we will have fruitful sessions and this gathering produce remarkable outcomes for the betterment of humanity. Thank you.
Now, ladies and gentlemen, it's my honor to invite our distinguished guest, keynote speaker, Professor Dr. Gerardo Carvajal, Professor, Department of Mechanical Engineering, Florida Polytechnic University, USA, for the inaugural address. I welcome you, sir, for the inaugural address.
First of all, I would like to thank to the chief patron, Dr. Nayer, chairman of the SCMS School of Engineering, Professor Pramod Devanur, vice chairman of the SCMS School of Engineering and Technology, Dr. Pravachat CJ, the principal of the SSET in Alkulam, India, also to the organizing committee, Dr. Vijay Chandran, Dr. Raj, and Mr. Noel Joseph Gomez. Also, I'd like to address this presentation to all the faculty members in the university, to people from the academia, the government, industry, and to all the participants attending this event. For me, when Dr. Raj invited me to address this event, I feel so happy. I say, good, because once I visit India in 2012, so to deliver an address there, so I enjoy being in India. So I think any opportunity I have to present, I always am happy, glad to share some of my knowledge with you, all of you. So for this address, also I like to highlight to one person that introduced me in this world of the numerical method, Dr. C.B. Shobhan. Dr. C.B. Shobhan was my co-advisor in RPI in New York with Dr. Peterson, famous a professor in heat pipes and Dr. Chauvin, expert in numerical simulation, was the person that introduced me in this world of the numerical method. Till today, I still are working in that area, so but I like to also address and acknowledge Dr. Chauvin for introducing me in this fascinating world of the numerical methods. So with this information, once again, thank you all for attending this conference. So I will address my presentation. This is kind of short inaugural address. I was inspiring this address, especially for the students that are working on this area. Probably some students, they don't know about this, what is computing simulation, numerical simulation. So for this presentation, my focus was trying to give you some overall an overview of different method computing technologies that you can apply for solving numerical method. So as an introduction, so when you review, when you are solving a problem as an engineer in the academia, every day we face problems. We need to solve problems, physical problems, okay? But in the academia, in order to do solving model, we need to apply some theory, okay? So in order to apply, to solve the problem, we need to model the problem. We need to apply some physical condition, or to apply some, to isolate the problem, and see what are the fundamental variables that apply for this problem. So in this introduction, okay, so I bring some good ideas from the Woods and Perth that talk about a model, because when we are doing simulation, actually we work with a model. We are pretending to solve the original problem, but what we are solving is a model, where we apply most of the variable, most of the physics, but it still is a model. So in this case, what is a model? So what is a model in numerical simulation? Is, according to this author, I like this definition, is a simplified representation of some real object or physical situation that serve, okay, to serve a particular and perhaps limited purpose. For example, when we were kids, so we usually imagine, when we're kids, imagine any object, okay? For example, we play with modeling clay. In my case, when I was a kid, I used, any object and I start playing with car. I imagine this is my car, I start playing, okay? Because we, as a kid, we apply modeling, okay? So with simple, object. So a child apply his imagination for modeling, okay? When he used any object as a toy. In our case, in the field of mechanical engineering, I think it's possible to also model a problem by applying mathematical expression and also verifying the physical law, the governing equation. For example, when you're modeling, in this case, the oscillator, harmonic oscillator, or pendulum with a mass. So how do you model this problem? How do you model the displacement, frequency? So in order to model this problem, okay, you need to isolate the problem. So how do you isolate the problem? You apply the governing equation, okay? For example, you can apply the simple model, could include only mass and spring effects, Model one. Also, the second model could be, you may include the, probably the many more components, like not only the spring, also the damping dissipation and perturbation, for example, So this model, with this mathematical expression, what you're doing is trying to represent this actual physical problem into this governing equation. If you solve this problem, you will get information about the displacement, oscillation, and many useful information. That is the idea in mechanical engineering, when we solve a problem, modeling. So the most simple cases for modeling ordinary or first orders OD, as we learned, are the Euler method, Runge-Kutta methods, Allan-Moulton method, and the numero method. So this method, actually, the last two methods apply for prediction correction methods. So this first orders OD. So we use this simple method when we have some simplified problem. We can apply this tool, okay, for solving a problem. So, but in this slide, you will see when you as a student or you're in academia, you will see what tools you can apply for solving a problem, no? So, because you can see, you can hear, no, there are many tools. So here, in this presentation, you will see the most common computational method for solving problems. So you can see, you start from the left, Monte Carlo simulation. Okay, so this technique apply statistical integration. So it applies actually for a stochastic problem, no? In this case, it's depending on chance. So we apply this method when we are dealing with stochastic problem, okay? Also, there are some particle methods. In this case, for the particle method, for example, the bodies are simulated by point masses. Molecular dynamics, okay? So in this case, you apply this method for simulating molecular scale models of matter. Okay, you may model, for example, condensation, vaporization at a small scale with very lots details about the process. Also, you can go beyond, no, and model a real galaxy, no, with approximately 10 to the 11th, okay, of star or very massive, for example, no. So this is kind of large simulation, no. Also, you can model also plasmas. You're modeling ion plasma placed in electric or magnetic field. So this is another area of specific modeling plasmas. Also, lattice Boltzmann method, no? So this method is gaining popularity recently. So this method is based on microscopic model and mesoscopic kinetic equations. So this method, LBM, is relatively new approach to simulating CFD. So there are many software that are trying to implement this powerful technique, LVM. Also, you are dealing, for example, with acoustic, with vibration. Okay, you may deal with the Fourier transformation. For example, this discrete Fourier transformation, when you apply one-dimensional Fourier transform in the region from x equal to 0 to 1, or fast Fourier transformation when you use a linear combination of this Fourier transform. Okay, so we can also deal with the finite difference method that lie within a continuous model. So we apply a discrete solution of either ordinary or partial differential equation. When you apply a discrete solution, we are dealing with the finite difference method. The control volume is another method. Some say this part of the finite volume method. What is the difference? That we apply a balance of fluxes. No? We create a small control volume and we apply energy balance, mass balance to a tiny control volume. Then we derive the equation from this modeling. Also, we have the finite element. The finite element, the approach is based on the error minimization of multidimensional PDF solution. So these are the most common, no? But recently, okay, so you can see probably complex models, CFD, okay, quantum computing, machine learning, algorithm, hybrid method. Okay, so this is kind of an overview. If you are a new student, a PhD student working in the academia, so you will see, that depending on your application, you are dealing with particle, you are dealing with small scale, you have this choice, different choice. If you're dealing with continuum mechanics, probably it's good find a different method or control volume or find elements. Okay. So recently I attended a virtual seminar from NSF. So I'd like to share with you, this important information from NSF. It was in this summer, in July. So in this, because we are in the area of mechanical engineering, so you can see here the main topics that NSF is promoting in the academia. So when NSF, when I attend this also virtual conference, NSF highlight the major topics, that for mechanical manufacturing. You can see advanced manufacturing, dynamics, control and cognition, optimization and design, mechanical and engineering material, and resilient and sustainable structure. But the most important part from these areas is that the manager from the NSF, they highlight the need for quantum science and engineering. Okay, so the manager this NSF branch mentioned that there are a lot of workshops about quantum engineering, quantum mechanics application. So the idea is what? The idea is to apply this new quantum phenomenon, no? To create a breakthrough in areas such as sensing, measurement, computing, and simulation. So quantum science is right now is a hot topic in the NSF. There are many proposals. If probably if we can probably have some collaboration with some of you, will be great. No, but this is an interesting area that you may explore. Quantum mechanics. Also, quantum algorithm is also important. In this case, quantum algorithm has received advances in terms of hardware capability, algorithm development, and availability of software. One of the most compelling applications for quantum computing is the idea of simulating quantum systems with many degrees of freedom, such as molecule and material, which is intractable on ordinary classical computers. So for this quantum computing, we need powerful supercomputer. So that's probably the challenge, okay, for using this quantum algorithm or quantum simulation. So quantum computing is different from classical computing. The best way to obtain quantum advantage is quite often subtle, okay? So it takes creativity to develop algorithms required to solve practical problems via quantum computation, okay? And although there are many progress, but still there are open questions and obstacles to overcome before the power of quantum computing can be fully harnessed for application in chemistry, physics, material science, mathematics, statistical, and computer science. Okay, so actually there is a lot of interest from NSF. Most of the topics are around quantum mechanics, quantum simulation. Okay, so this is a new, that is not new, but is the NSF highlights a lot of research in this area. Also, machine learning method is also in the past 2 or 5 years is increasingly applied in many areas of mechanical engineering. Okay, so the idea is that machine learning use computer algorithm to make forecasts. Okay, for example, for facial recognition, okay, they use a machine learning, but the machine learning now is being applied in mechanical engineering. Okay, so the idea is, you can see here, no? This program, when you run, for example, this is for computing the critical, the temperature on the wall under critical heat flux. The traditional way is to develop a program, no? Develop a physical model, mesh, boundary condition, and so on. So then you perform this calculation. But if you use machine learning method, you basically use a series of algorithms. You have data, some information that this algorithm will create kind of a data bank, no, of information. Then from this information you can get your results. Okay, so how good is this method? According to this paper, for example, no, in this study they applied 10 by 10 by 10 neurons, and they compare with the experimental data, and the error RMS is within 2.35 Kelvin. No? If you increase the number of neural network, this error decreased significantly. Okay. Also, when they compare this result from machine learning with the traditional ways, so you can see there is not much difference. So this is kind of promising, tool for applying this machine learning in heat transfer. Also, the last recently also attended the Summer Heat Transfer Conference. During the Summer Heat Transfer Conference, also during the address of this machine learning topic, for example, this the chair of the session mentioned that he developed a CFD work with the machine learning. So for CFD, you need to apply some mesh, you need to develop the physical model, but with machine learning, CGAN is one machine learning method, you don't need that. But what you need is kind of training. You need some data in order to storage. Based on the data, then the program starts solving the problem. In this case, they solve a two-dimensional temperature distribution in a flat plate and compare these two results. The advantage you can see here is not only is accurate, but also time. No? You save time is almost the speed. Solving this problem is faster than traditional method. And so the machine learning, as I mentioned, and quantum computing are the two recent tools that are being used a lot recently in the area of mechanical engineering. But also in this presentation, I will also mention the traditional way, CFD, that is used also for solving problems. Now, many of you probably are familiar with CFD, but my idea is to provide kind of an overview for our student, new students that are trying to pursue, that are trying to work in this area of computing. So what is a CFD? According to John Anderson, the CFD is the art of replacing governing partial differential equation of fluid flow with numbers. So, and advancing this number in space and or time to obtain a final numerical description of the complete flow field. So this is the art of solving. So the problems are so complex that it's almost difficult, hard to get analytical solutions. So, but by applying CFD, it is possible to solve complex problem, linear or nonlinear problem. So this is the CFD, the art of replacing. With CFD, we can, as it was mentioned by the Dr. Pravasan, so you can get CFD result with relative low cost compared with experimental tests. Okay, much of the aircraft industry, the testing of preliminary design prototype is almost done entirely on CFD code. Okay, but in this case, the key part that allow practical growth in CFD is the presence of high-speed computer, supercomputer. Without computer or supercomputer, is impossible to continue advance in the area of CFD. So but in order to deal with CFD, there are three fundamental principles of governing equation: mass conservation, Newton's second law, and the energy equation. This is kind of the three physics that we apply for solving CFD problem. So also the CFD is called as the new third dimension in fluid mechanics. The other two dimensions are pure experimental and pure theory. Okay, so the numerical method or computing or CFD software are so powerful that the accuracy is good, is very good. Okay, so therefore, okay, is considered as the third dimension. So is we can trust in the numerical method in CFD. So we also compare with pure experiment and pure theory. So this is the important part. This is the roadmap for CFD. You can see in CFD we solve mass conservation, Newton's second law, and energy conservation. So depending on the, you can see here, model of the fluids, you may have fixed control volume, moving final control volume, fixed infinitesimally small volume, or moving the infinitesimally small volume. So you may apply any of these different control volume and any numerical method. You can see here, you may apply finite difference, finite volume, finite element, lattice Boltzmann, hybrid, or many different methods. Also here, they're trying also to apply here the machine learning. And so depending on this method, for example, we will see later that, for example, console, they use finite element. Fluent ANSYS, they use a finite volume method. Depending on this numerical method, you may be able to solve the problem. So you can see once you use, yeah. Have any question? Okay. Simplification. This is the simplification of the Navier-Stokes equation. When we are solving the CFD problem, we are dealing with we have to solve the momentum equation or the Newton's second law of motion. You can see here now the different possibilities about the Navier-Stokes equation. Okay, so we can simplify the, for example, dPdy, dPdz if you are dealing with laminar boundary layer. Also, you are dealing with zero kinematic viscosity. You have the Euler equation. If there is zero acceleration, you are dealing with Navier-Stokes equation. So this is kind of the roadmap for dealing with Navier-Stokes equation. Here, I will not talk about the turbulent models, but this is kind of general overview. So it's important, no? If you are dealing with CFD, that is the most popular tool for in the academia industry for solving problems, you may ask, no, what is the best CFD? So it depends, no? So here you can see some history about the CFD. In the past, took many years for solving problems, but today we can solve complex problems in a few times, no? Few seconds, depending on the complexity. So in the 1947, Copal was the first researcher to solve numerically the continuity momentum equation. Okay, using a primitive digital computer from MIT, this person solved numerically, the continuity momentum equation. Between 1950 and 1960, it appeared the first generation of CFD solution for higher speed and higher temperature. You can see, that the CFD. Also, you can see here how the computing time has decreased with respect to time. This is the relative computational time, okay, per year. So in the 1960s, appeared the time-dependent technique created a revolution in flow field calculation. After this, 1960, okay, you will see a rapid increase in many CFD software. So this is kind of an overview, and I will show you in this last part of my presentation some tools for using. If you are a PhD student, there are many CFD codes free that you can use for free. Okay, you can see OpenFOAM, SU2, PyFR, Code Saturn, Phoenix. I have one colleague in Florida Poly that used SU2. Okay, I also, when in 2018, I visited the University of Oslo, the Department of Mechanical Engineering, the group in Oslo, they use Phoenix as a free software. So this is, you have, many free codes that you can use. Okay, so if you are interested in using a free code, it's fine. Okay, you can use this software. Also, we have commercial software, like you can see Console, Numeka, Flow Science, NCs, Total Simulation, Metacom, StarCD, and so on. Okay, so the advantage of using commercial software, you have technical support, you have the meshing process, post-processing, and so on. That is the advantage. So, but disadvantage of using free software is that you need another software for plotting, post-processing. Also, you need another tool. If you're using free software, you need some mesh generation code. Okay, you can see GMS, you can see Engg, you can use NetGen, Retizer. Also, for visualization, you need another software tool for presenting your data. This is the free software ParaView. Also, you may use OpenDX, Maya, and TechPlot. This is only some of examples that you can use for dealing with numerical methods. So I conclude with this slide my presentation. Thank you very much for this brief, short overview of the computational method and the CFD, okay, analysis tool that you can use in your life, as a PhD student, master student. Okay, you can solve complex problem. Okay, we need a student like you, a PhD student, master student that address or solve the complex problem by applying the fundamental law of physics. Thank you for your attention. If you have any question, please, you may ask any question.
Someone very rightly said, gaining knowledge is the first step to wisdom, and sharing it with others is the first step to humanity. Thank you, Professor Dr. Gerardo Carvajal, for sharing valuable ideas with us today. Thank you, sir.
Thank you.
As we move on, ladies and gentlemen, now we have Dr. Anita G. Pillai, Dean Academics and Professor, Department of Civil Engineering, ICCME School of Engineering and Technology, for the felicitation address. I invite Dr. Anita G. Pillai. Ma'am, please, over to you.
Dr. Anita, I think your mic is off. Please unmute.
Okay. Sorry. Thank you, Mr. Sanju. A very good morning to the distinguished resource persons, invited participants, my fellow colleagues, and dear students. 18th century will go down in the annals of history for spurring a revolution in the field of engineering and for the proliferation of the much abused term globalization. The first industrial revolution used water and steam power to mechanize production. The second used electric power to create mass production. The third used electronics and information technology to automate production. These words of Klaus Schwab, the founder and executive chairman of the World Economic Forum, the International Organization for Public-Private Cooperation, overtly describes the transition made in the computation of myriad scientific processes and in the field of production. All the stakeholders involved will undoubtedly state that irrespective of technology adopted, all the methodologies used to improve productivity was focused on transforming existing practices easier. The word easier was redefined over the years by incorporation of computers, whose overarching presence have transformed the facets of mechanical engineering and paved the way for another revolutionary concept, Industry 4.0, which is acting as a catalyst in the ongoing automation drive. With digitalization gaining a huge fillip in various educational frameworks, initiatives akin to ICCME 21, organized by the Department of Mechanical Engineering, ICCME School of Engineering and Technology, is commendable. Wishing a huge success to this conference and an enlightening learning experience to all the participants. Thank you.
Thank you.
Thank you, ma'am. Ladies and gentlemen, moving on, it's time to propose the vote of thanks. May I request Dr. Vidya Chandran, Organizing Chair, ICCME 2021, and Associate Professor, Department of Mechanical Engineering, ICCME School of Engineering and Technology, to kindly come forward for putting forward the vote of thanks. Dr. Vidya Chandran, please.
Thank you, Mrs. Sanju. Respected Chief Guest, Professor Dr. Geraldo Carvajal, Professor Alam Mohammad Mehboob, Professor Dr. Praveen sir, our principal, Dr. Anita G. Pillai, Dean Academics, ICCME School of Engineering and Technology, Dr. Rag, Professor and Head of the Department Mechanical Engineering SSCT, other dignitaries, respected authors, participants, dear colleagues, and my dear students. It is indeed a moment of pride for our institution to host this conference with stupendous participation from the computing enthusiasts of mechanical engineering. I count this opportunity as my honor and privilege to thank each one of you for being a part of ICCME 21. Let me first thank Professor Carbajal for kindly accepting our invitation to inaugurate ICCME 21 and address the gathering. Thank you, Professor.
Thank you.
Professor Gopakumar sir has always been with us from the very beginning of the conference preparation, and I take this opportunity to express our sincere gratitude on behalf of the Department of Mechanical Engineering for his guidance and support. Due to some unavoidable assignments, he was not able to join on this occasion today, but I still thank you, sir. Thank you so much. And I also thank the SEMS management for giving us all support in hosting this event. Dr. Praveen Salsar, our principal, as always, has helped us uphold and reflect the morale and ethics of our institution in hosting this prestigious conference. Thank you, sir, for being with us and for all the guidance provided. Next, I would like to thank Dr. Anita ma'am, Dean Academics. Despite of her busy schedule, she was always there to help us whenever we needed her advice. Thank you, ma'am, for being with us and addressing the participants. Dr. Rag, our head of the department and convener of ICCME, is the backbone of this event, and words won't be enough to thank him on this proud moment. Thank you, sir, for guiding us through and making this day happen. I take this opportunity to thank Dr. Shija Janardhanan, our former head of the department, who had initiated this conference in 2015 and had elevated it to this prestige. Thank you, ma'am. And I thank all our authors who are the real contributors of this conference for nourishing the conference with your valuable research findings. I welcome you to this great knowledge sharing platform and wish you 3 fruitful days of great learning. I take this opportunity to thank Ms. Colinda and her team from Cadence Numeka, who has collaborated with the conference to provide a hands-on session for the participants on the multiphysics computational software Omnis 5.1. I extend my sincere thanks to the faculty and students of our institution who has joined us on this inaugural ceremony and request you to be with us all through the conference. Thank you all. Thank you for coming and joining us, and have a good day. Thank you.
Thank you, Dr. Vidya Chandran. It's time to announce the end of the inaugural ceremony. Now, ladies and gentlemen, we have the start of the keynote session. We have the first keynote address by Professor Dr. Gerardo Carbajal. Ladies and gentlemen, now are the time that I take the opportunity to invite Professor Dr. Gerardo Carbajal for the keynote address.
Thank you very much for, again, the introduction. I will deliver my presentation, my keynote presentation. Can you see my presentation?
Yes, sir.
Yes, sir. We could.
Okay, good. Yeah, thank you. Yeah, thank you once again for inviting me for this important event. As I said before, it's an honor for me to be part of this event. And today I will share with you one important topic, that is transient heat dissipation of the flat heat pipe thermal spreader, a mathematical modeling and simulation. So the outline of my presentation is, I will show you the introduction, I will show you the heat pipe operation, I will talk about some porous medium, working fluid, heat pipe applications, fundamental principle, mathematical modeling, transient heat dissipation of flat heat pipe, thermal spreader, numerical result, and conclusion. So this is the outline of my presentation. You have any question, please let me know anytime. You can interrupt me, okay? Introduction, heat pipe application. This is as part of motivation prior to starting my topic. So I select send 2 or 3 key topics. So I may assign a question to my students. So in this case, prior to my presentation, I will show you the some application of heat pipe, for example, in electronic cooling. Why heat pipe is important in electronic cooling? You can see you have you have a heat pipe. In this case, for example, here, you may have different heat source. This on red is the you have a heat source, and this is a heat pipe. The advantage of heat pipe is you can dissipate heat, okay, evenly in this system. Here you have some things that may help you to dissipate the heat from top to the bottom surface. So heat pipe, you can see this is the sketch. If you apply a cross section, you can see how what is inside of the heat pipe. No? You can see some components, some wick, some vapor core, and some solid material. And here on red is the heat source. Also, a heat pipe also is applied as a thermal for storing energy. Okay. In this case, you use PCM materials, okay, for heat pipes. Here you have a 2 millimeter thick loop heat pipe. That this is this technology is applied for heat pipes. And also here you have the loop heat pipe. This is the traditional loop heat pipe that we use on laptop computer. So you can see that also the size, no, is you can perform a heat pipe at small scale. So a heat pipe is applied a lot in the electronic cooling. Okay, you can see more application of heat pipe, but also there is a recent application, a lot of application in battery cooling management. Okay, so as you can see in the United States, also in Europe, there are some in Europe, no, they're planning to stop the combustion engine production by 2030. No, in the United States, still there is not a definite date, but the government is pushing, no, to all the funding to create kind of green energy, to move from internal combustion engine to electric energy, sorry, electric vehicle. As you can see here, no, this is the electrical vehicle here that replaces the internal combustion engine with a battery system. You can see here, no? So, but you have, the problem is you have a battery, so there is a lot of heat generation. So you cannot use a battery without any cooling system. So the heat pipes is a promising technology that can be used as a passive way to dissipate heat here, no, from this battery system. So this is one design. This is another design of heat pipe. In this case, you can see in this case some cool heat pipe exchange system. Also here, no, another schematic of a heat pipe, no, like a siphon heat pipe that also is used for cooling the battery. So this is a topic that recently there are many research done, no, trying to reduce or mitigate the heat generation in batteries. As you can see, this is only 2 examples, okay, that you can see, no. So, okay, what is a heat pipe, no? How does a heat pipe work? How do you dissipate the energy, no? That's the idea, no? With these 2 example introduction, I will share, I will start my topic, heat pipe operation. So in this sketch, if you are not familiar with heat pipe, what is a heat pipe? A heat pipe is a closed system, no? A closed system that utilizes working fluids. Could be any fluid for evaporation and condensation. A heat pipe is a passive system, closed system. The heat pipe operates in a closed 2-phase flow cycle. There is only one liquid and vapor are present in the container. Let me show you. This is the typical, for example, sketch of a flat heat pipe. You can see on the blue color is the solid material. The next layer is the weak or porous media. And in the core is we call the vapor core. Okay. When you apply heat to the heat pipe, so this is a closed system. So what happens? No? Then the heat dissipates by conduction through the solid material, and then here in the weak material, because if we have some fluid inside of this porous media, the fluid vaporize here. No, is you have vaporization, so then you keep the temperature at some level. Okay, then this vapor move to the colder side where it condenses. In this colder side, then the fluid or liquid vapor condense, and by capillarity effects, okay, because this is a porous media, then the liquid fluid return back to the heat input or the heat source. So, and then you may have a continuous operation. No? That reason that we call a passive system. You don't need any external device to operate. The only condition is that you have to be careful, no? That the heat input to not overcome the critical heat flux in the system. There are some other constraints, okay, in order to guarantee a passive or continuous operation. So this is a heat pipe, okay, a combination of solid material, weak or porous media, and the vapor core. So then here it happened the heat rejection, okay. So also you may apply a thermal resistant model to study, no, that conduction, vaporization, condensation through this system. So this is the fundamental idea of a heat pipe. Okay, other type of heat pipe work in a similar manner. Okay, there is a heat input and heat rejection. Okay, so it's important to highlight, no, that here in the vapor core in this area only have vapor, and here in the wick you have liquid. As I say here, no, closed system that where liquid and vapor are separated. So this is in this study. Okay, so when you design a new heat pipe or a new passive system, it's important to identify the output. Now, what is the output? So what is the input? Okay, what do you need? Why a heat pipe? No, are you planning to design a heat pipe for cooling batteries, for electronic cooling, for a heat exchanger? Okay, for any purposes, you have to identify. Okay, then you have the constraint, no, as any other design, control variable, geometry. What is the best geometry? What are the dimensions? What should be? What is the size? No, sizing. What should be the length of the heat pipe? What should be the thickness of the porous media, for example? No, how much should be the porosity, the permeability? Material selection. The material selection and working fluids is important. No, all these variables or parameters are part of the design of a heat pipe. A heat pipe is a system. Okay, so you can see here, this is one. In this case, I work with this particular flat plate heat pipe. You can see here, no, the final concept of the heat pipe. You can see, no, the cross shape, and here, you can see here the weak material that is around this cross shape. No, so then inside of this system we use water for using the heat pipe. Okay, so this is the constraint, the limitation. Then based on this, in the requirement, on the need of the client, industry, and okay, then we can start working. So when you are doing a heat pipe, first it's important to understand the physics of porous medium. Okay, so depending on the porous medium that you may apply metal foam, for example, a fibrous material, fractal, carbon felt, for example, carbon felt is used, for example, in proton exchange membrane. So depending on these materials, so then you start with the first important parameter in heat pipe, the porosity. Okay. So the porosity is a property of a porous medium that is defined as a fraction of total volume of free space respect to the total or solid material. Okay. Total material plus the empty material or fluid. So the ratio of the empty to the total volume, this ratio is called porosity. The porosity is greater than 0 and less than 1. No? We have another property called permeability. Permeability is a measure of the ability for a fluid to permeate on the material. For example, you pour water on a paper, it hardly water will be dissipate on the paper. No? But you use for example, a paper towel, you apply water spread quickly, no? So that is the permeability, how fast, quickly the fluid is permeate on the substance. So the property, this K property, okay, we use this, we can relate K with these properties, this velocity, mu is the viscosity, okay. Del P is pressure, L is the length of the thickness. Also, for modeling a heat pipe or the porous media, you can see when you are using porous media, you may use a fluid, okay? Metal foam, fibrous material, fractal, solid material plus a fluid. So you will have a combination of solid material and fluids. So the challenge is when you are modeling the porous media, okay, you may replace the effect of metal or the solid part and the fluid as a single material. In this case, you may apply the definition of the effective thermal conductivity. Okay, this thermal conductivity measure it take into account the presence of the porous media, porosity, and the presence of the solid material. Depending on, there are different models, okay, for computing the effective thermal conductivity. So once again, it depends on the type of porous media. Also, the mean specific heat, because you have the solid material and porous media, also we may apply, this is kind of the standard way of computing the mean specific heat for porous media. So these four properties is extremely important when you are dealing with heat pipe. As I mentioned before, depending on the material, there are different models for computing. So this is in this case, you have the diameter. You may obtain some correlation for computing the corresponding K or permeability. This part. There are different models for approximating the effective thermal conductivity. So depending on this model, you will get a good or bad result. So you have to be careful when you're selecting the corresponding model for the effective thermal conductivity. You have to do some research first to make sure that if your porous media, okay, what model is the best for your porous media, okay? Also, working fluids. In this design, in this analysis, the flat heat pipe operate within 300 to 320 kelvins. Sorry, Celsius. Sorry, so this 300 Celsius is the limit. So in my case, the limit is we work within 300 and 350 Celsius. Is the maximum temperature that we expect on the surface temperature. So this working fluid, it tells you, you can see here, there are different fluids on the left, on the right. You can see the fluid on the right are for high temperature application. But for middle, like for 300, in this range of temperature, you have water, you have acetone. For low temperature, you may have helium or hydrogen. So in my case, okay, I use water as a working fluid, no? This is depending on the operating temperature. So you are designing a heat pipe, you have to do this exercise. You have to check all the working fluids and find the appropriate operating temperature range. But not only selecting the fluid, we'll see later also you have to see if there is some compatibility between the fluid and the solid material. When you are selecting a working fluid, not only is important the operating temperature, but also the number of merit. Okay. The number of merit, you may see here, number of merit N is equal to the product of density times surface tensions times latent heat divided by the dynamic viscosity. This is a dimensional parameter. This product actually gives you an idea that what is the best working fluid for your case. We select the working fluid with the highest N. For example, you compare water, for example. Here I have 8 fluids. Water on top are 1, 3, 4, 8 on the bottom, 1 to 8. If you apply this equation and plot the working fluid for a different temperature, okay, you will see that water is on top. Water has the highest number of merits. So water is a good candidate for many heat pipe application. So this is a dimensionless expression of the number of merit. This is based on the number of merit of water. So this is kind of dimensionless, okay? When you divide by N for water. So this is important, no? That number of merits, the highest value is the best for your application. And also, not only the number of merits, also is important to check the saturation of the vapor pressure. For example, you can see this number 1 is ammonia. So what is the problem with ammonia? The problem with ammonia is that you are working, for example, with 300 in the range between 300 to 400 Kelvin. Unfortunately, you're dealing with ammonia as a working fluid. Pressure rise suddenly so fast that you may experience the internal pressure may increase dramatically. Okay, you can see this is in megapascal, is the y-axis. Okay, so you have to be careful, no? Because the heat pipe is a closed system. If you apply heat, please remember that pressure may increase. That's the pressure. So in this case, if you see for water, because I interested in water, is here is 8. I'm not sure you can see 8. You can see here 1, 2, 3. Okay, 8 is here. This is 8. You can see the temperature is almost, the saturation pressure is almost steady within 300 and 400. No dramatic change. It only changes significantly when you are closer, closer to the critical temperature, for water. But in the low range, water is a good candidate because the saturation pressure is less than ammonia. For example, ammonia has a higher vapor pressure. So this is another parameter. This is the liquid conductance. The liquid conductance is the number of merit, but in this case, they multiply to the number of merit by the thermal conductivity. So in order to include that the effect of the thermal part, you multiply by K, and by K is the liquid conductance. So this is the liquid conductance for different fluids. You can see here. There are some fluid that has very good liquid conductance, other has very low thermal conductance. Okay, you can see here without therm G and A. So these are fluids that has a very low conductance. So these fluids, okay, we may discard for my application because it's too small this value. As I mentioned before, it's not only important selecting the working fluids, also the material. What is the case material? If you're working with, for example, with water, you cannot work with aluminum. For example, here you can see in this table, you can see the C is compatible. For example, aluminum and water is one, mean is incompatible. You cannot use aluminum with water, okay? But you can use water with silicon. Is C is okay, or water with nickel. So you have to be careful, no, about this table, or check in the literature review the specific, compatibility within your working fluid and your material to ensure that there is no corrosion. Because if there is corrosion, if there is a redox reaction, the problem is that you may generate some gas. This, for example, is a contaminated magnesium alloy sample. You can see here this like a dark color here is a corrosion. No, here there is a redox reaction. So the problem in redox reaction is that you are generating hydrogen here. No, so this hydrogen is fatal for heat pipe. You cannot create or having corrosion when you are dealing with heat pipe. Okay, so then once again, as an overview, it's important first to select the best porous material. That's number two, selecting the working fluid having two parameters, no? The saturation pressure and the number of merits. And select the working fluid also depending on the selection of the case material or weak material to prevent corrosion inside of the heat pipe. Because if there is corrosion, there is gas generation. That it will damage or will destroy the performance of a heat pipe. Okay, with these fundamental ideas, okay, we can say, no, like any problem. So here the problem is to design a heat pipe, that it will operate with transient operation. That then here we need to apply some model, no? How you will address, you solve this problem, no? Then we need to apply the fundamental principle, mass conservation, Newton's second law equation, or the momentum equation, and the first law of thermodynamics, or energy is conserved. Okay, so we apply this fundamental principle for the modeling the heat pipe. So modeling heat pipe actually is not easy, it's difficult. It depends on the geometry. It also will depend on the operating condition. It will be stationary or will be moving. It's going to operate in transient condition or steady or periodic. So it's not easy task, no? But you have to make some assumption in order to get some important results. Okay, it's important also to be careful, no? Identify all the physical model that your system may experience, okay, in order to get an accurate model. Sometimes we make assumption. So when we make assumption, sometimes we neglect some physics, but you have to be careful, no? As I said before, there are many types of heat pipe designed for many applications for terrestrial or space application. So there is no any unique CFD or any model, a unique model to solve all the problem in heat pipes. So in this case, probably one heat pipe has its own math formulation. Okay, so it's not like having a CFD code that you can apply to many different geometry. But for the heat pipe, depending on the particular application, you can apply that model to a different heat pipe application. And when you're modeling a heat pipe, so you have to solve the governing equation. No? The governing equation, so then when you're modeling heat pipe, so this is the continuity equation. You can see you have to apply this mass conservation for the weak and the vapor core, weak or porous media. For the weak, we assume like an incompressibility effect. So we have this equation, okay? But for the vapor core, okay, you may have some, okay, change in density. So we can allow a change of density over time. No? For the momentum equation, you use this single equation. In this is the momentum equation that account the Forchheimer, the Brickman, and Darcy's term. This is the the dark cistern, this is the Forheimer, and this is the big one. Okay, so this and this FB is any source, any force, no? Any force. It could be, for example, capillarity effect. So for the wick, for example, you have to compute, no, the corresponding porosity. And for the vapor, you use the same equation, but in this case, the porosity is equal to 1, and the permeability goes to the infinity, and that is force for the vapor core. You may assume in this case, for example, 0, no, because it's a simple case. But you can use this simple single equation for the momentum equation for dealing with the wick and the vapor core at the same time. You may, in your model, in your program, you may create some constraint, no, in order to use the same formulation. Similarly, for the energy equation, in this case, the energy equation, you're solving the three regions, the solid region, the wick or porous media, and the vapor region. You may use the same, once again, expression. You only may change if in your domain, no? Depending your domain is the solid material. If your domain is the wick or vapor core, you may change only the properties, no? For example, here for the solid material, you may replace the effective thermal conductivity simply by the thermal conductivity of the solid material, no? This is the mean specific heat. You may replace by the corresponding density times specific heat of the solid. So for the solid, V is 0, for example, no? And in this way, also for the wick, you use effective thermal conductivity and the mean specific heat. And for the vapor core, for example, the K effective is equal K of the vapor, no? And Cm or mean heat capacity is equal to rho C of the vapor. So in this way, the idea is to simplify the modeling, no? So you use the same equation for solving at the same time the solid, wick, and vapor, only by changing this variable in your code. As I said before, no, when you are dealing with a heat pipe, so the thermal analysis CFD is important, but also it's important performing the thermodynamic modeling, because you need to size, you need to determine the dimension, or what dimension is appropriate for this application. The only way by doing that is by applying a thermodynamic model. So this is the flat heat pipe for transient application, then let's compute, no, the effect of the dimension. You can see H, L, W, del wall are the corresponding dimension of the volume. F is for the liquid and G is for the vapor, no? So you can use these dimensions to relate the dimension, how this parameter can affect the energy balance. Here apply the first law, the energy balance. Okay, you can see. So this is, you model the heat pipe. You can model heat pipe as a closed system with some amount of liquid and some amount of vapor, no? If you have heat transfer, heating, and cooling, then you can model this simple thermodynamics model by using the dimension, no, of the potential heat pipe. So then when you apply the energy balance, the first law of thermodynamics for closed system, then you may compute or estimate the internal temperature for the final state. Here, U2 is the internal energy for the final state. So you, based on the heat input, net heat input, okay, then you may find the temperature. Okay, so in this case, because this equation is include not only the thermodynamics properties, but also the dimension, the physical dimension of the heat pipe, then you can find the temperature, T sub 2, in terms of the dimensional parameter. Okay, so this is state 1, and this is the final states. You can see here in this result, when you apply the thermodynamic model, you can see here how it allows you to see, what happens if you, for example, change the thickness of the porous media. What happens if you increase or decrease the thickness. So here you can see if you increase the thickness of the porous media means that you are moving closer to the saturated liquid region, for example. No? Why? Because if you increase the thickness of the porous media means that you're getting a thicker region that contains more water than vapor. Okay, if the thicker has the same dimension of the vapor core, means that the entire vapor core is full of liquid, so there is no empty or free space for the vapor flow. Okay, that's the reason that this in this point represent the direction. No, if you thicker porous media means you are closer to the saturated liquid. So thinner porous media means you're closer to the saturated vapor. Okay, so you have to find that. Okay, the optimum value. Okay, optimum value for the thickness, for example, here. No. Also, you can use investigate pressure. Okay, so using this parameter from thermodynamics, so we may be able to estimate, for example, no, this intersection allows us to get the ideal thickness, for example, no, for this particular application. So once you apply the thermodynamic model, then you come up with a basic dimension. You can say, so this pi must have this, for example, length. It should be L, the width W, height this value, the thickness of the porous media should be this value. So then you start with this input from the thermodynamic model. With this input, then you may use this information to build up your numerical model, to check, to validate if these values are acceptable, no, from the numerical simulation. So like any physical problem, you have to make a selection, no? So for example, if you are this assumption, you have to make an assumption in order to simplify the problem. The idea is to minimize the assumption, no? But in order to simplify the problem, most of the time we make assumption. So in this case, for example, you may assume natural or forced convection at the condenser size. Is this natural convection or forced convection? You may have a different, outcome from the heat pipe. The ambient temperature is held constant. For example, is working in the heat pipe in a summer condition most of the time, or is working in an environment where the temperature change, for example, no, from summer to winter, or a place where daily there are some daily rains. For example, in the morning probably it's too cold, in the evening probably it's too hot. So you have to be careful, no, about this ambient condition in effect. Also, you may apply radiation, gray or black surface for in electing or including the radiation effects, laminar flow, turbulent flow, compressibility effects, or incompressible dissipation effects. For example, in this case, in this problem, in my model, I neglected dissipation effects to simplify the governing equation. So also it's an important assumption that in this any heat pipe must operate below the critical point, okay? Critical heat flux. Otherwise, the heat pipe may explode, no? Because if you are working near to the critical heat flux, okay, the heat transfer will increase the pressure, and then it may be risky using that heat pipe at critical heat flux. Okay. Also, you may assume isotropic and isotropic porous media, variable constant material properties. There are some, for example, research that they, for example, consider that K, the thermal conductivity, change with temperature, for example, or they assume constant property. No, you assume constant property, you may have different outcome or variable or properties that change with temperature. Okay. Saturation condition, for example, at the liquid vapor interface. So, for example, this is important. No? Ideal gas model in the vapor core. Okay. You may apply different model. It's okay. Different. There are many models in the literature for the vapor core, and also the initial condition, no, for the system. Also thermal equilibrium. For example, you are dealing with a thermodynamic model, for example, no. And then you have the boundary condition. Okay, so the complexity of heat pipe is that in order to state the boundary condition, you have to apply the boundary condition to 3 domains: the solid region, that is the external, or is the case material, the weak or porous media, and the vapor core. Okay, you can see here, no? Depending on the so this is the evaporator walls. Here is when you have the heat input. So you can model, for example, this is, you can apply this equation heat flux from the, this is the heat source equal to this, the heat conduction, no, on the interface. Okay, you may have probably also a heat flux alpha beta means that you may have a non-uniform heat flux, for example, no? It may depend on the space dimensions. Then you may also equate with the, okay, with the thermal conductivity or heat conduction on the interface. For the wall weak interface, for example, no, there are different models, but in my case, I assume, no, that the heat by conduction at the interface between the weak and solid material is exactly the same. This is the heat conduction, no, exactly is equal the same at the wall interface, wall and weak interface. This is the condenser wall. So if you are the condenser wall, for example, you have a forced convection, or you may have also radiation. You may include radiation here, no, in this convective coefficient. So this is the heat by conduction that is leaving the system, and this is the cooling process, no, HT. Also, if for example, in the case of if you are dealing, for example, with a lithium-ion battery, probably one surface will be in contact with another surface, for example, no, cool surface. If you are not using a fluid convection, also you may use another surface, no, to dissipate the heat on the condenser wall. So it depends on your particular application. So also in heat pipe, the challenge is how do you model the interface, the liquid vapor interface. Okay. There are different models for modeling the liquid vapor interface. So you can see here, no, this is the interface. This is the wick. So you can see here, this is the heat pipe in a horizontal position. So inside the wick, so this is the wick. At the interface, you have some molecules, no, interaction, vapor interacting at the interface. How do you model? How do you account for this molecule interaction? So this is how you account for the net mass transfer, no? So there are different models, kinetic model, no, in order to best represent this phenomena at the interface. Okay, so this is one kinetic model that approximates, the velocity. This is the net velocity at the interface, and then here you apply the energy balance at the interface, and this is the Clausius-Clapeyron equation to relate the pressure at the interface with the temperature, no, between the vapor and the interface. The density, as I said before, is a saturation condition. I assume density at the interface at saturation condition to simplify the analysis. Then, by using this equation, you can approximate how much is the temperature at the interface. Okay, because here there is a discontinuity. It's continuous region between the liquid and the vapor region. Discretization method, control volume. So in my case, I apply a two-dimensional analysis for modeling this heat pipe for transient application. Actually, I apply a three-dimensional 3D quasi model. I will explain later. Okay. So this is only an example. No, when you analyze here, I analyze the interior nodes. Okay, so if depending on the size, no, of the node, you are del X and del Y are the dimension of this node. When you analyze this control volume, then depending on if this del X is equal to del Y, this beta is equal to 1. This N is the possibility of having some heat source in this interior node. Okay, you may have this equation if, for example, if beta is equal to 1, you have a uniform mesh, for example, no, along the X and Y direction. For interior corner also, when you do this control volume method, you may obtain the corresponding equations, okay, to relate the temperature, okay, for the corresponding node. As you can see, this process or methodology was applied for modeling this heat pipe. This is two-dimensional analysis. Also, this is another corner. Okay, so you apply the control volume, but here I simplify. I skip some energy balance. Here I only presenting the outcome after you apply the energy balance. This is the result, no? The corresponding temperature. But this model is from control volume. Okay. Similarly, for this, this is adiabatic. For example, you have adiabatic in convection, then you may apply this control volume analysis to determine the temperature in this node I, j. So, as I mentioned at the beginning, when applying the control volume methods, I'm using this mesh discretization in order to determine the relationship between the temperature of the surrounding node, for example. No? So this is the corresponding temperature. So this is an example about how you may deal with the discretization. Here I didn't include the discretization at the interface solid weak, neither the weak and vapor interface. This, okay, there are more, you need more detail, you can send me an email, no? I can give you more information, but this kind of an overview, give you an idea how you can discretize or obtain your equation. So then this is the particular case, how I solve the problem. Once I review the fluid, select the fluid, I select the material, I select the thickness and dimension of this heat pipe. The next challenge is to perform the numerical calculation. After we discretize the governing equation, and then we are able to solve this problem, okay? And so this is the challenge, no? The challenge is that this heat pipe is working a transient, all the time is transient operation. The first cycle for this heat pipe lasts only 30 seconds. 30 seconds, can you imagine? So this is a short cycle, no? So for this short cycle, we have to investigate the heating, also cooling process, that heat pipe. So this heat pipe, it may experience many cycles, no? Many cycles. That's the reason I call this is a transient heat pipe application. So this is in order to solve this problem, as you can see, so this model is for the heat flux. Okay, so this boundary condition here, to simplify this model, I applied only a two-dimensional model. As you can see, the actual heat pipe is complex. This is the cross-shaped heat pipe surrounded by this thin layer of the wick. So this is a wick material, this part. You have many cross-shape inside of this heat pipe. So, but this analysis was done in two-dimensional way. So if you plot, okay, what happened along this line? So this is the one simplification in 2D of the problem in 2 dimensions. So I assume here on top a adiabatic surface. So this input, as you can see, this input correspond to this non-uniform heat input applied on the left-hand side. On the right-hand side, we have a kind of uniform cooling system, no? Convection on the cold side of the heat pipe. Also, for this study, also we also develop an experimental setup, okay, in order to compare, validate the numerical result with the experimental data. Okay, so this is important. As I mentioned before, the numerical method is the third dimension, is reliable, but anyway, we conduct also at the same time some experimental data to make sure that if our numerical results are on the right track. Okay, so So you can see here, this is the flat heat pipe. You can see on the back side, there is a propane torch, and intense heat is applied on the heat pipe. On the back side, you can see a thermal infrared camera that record the temperature in the computer. So you can see here, you can read in transient way how this temperature increase over time. You can regulate, you can stop the propane torch, so therefore you are able to compute experimentally, also numerically, that this heat transfer on the surface. So when we applied this propane torch, there was a problem that we didn't know how to model the heat flux distribution, okay, from the propane torch. So we need, for the modeling, for the numerical simulation, we need this function of how to compute the heat input, because this is the critical part of our model. So in order to obtain this heat inputs, we apply what we call the hybrid numerical model. So what we do here in this case, what I did is to use the information from the experimental part. So I create this dimensionless model. This is kind of a correlation for dimensionless model with a constant C1. This is unknown. So in this correlation, account for the dimension. This is the dimension of the heat pipe. This is C minus 1C. So this is the dimension. So this is flat plate heat pipe, where Z and Y are you can see here, no, are the horizontal dimension, okay, for the heat pipe. But once again, using this model, you have two constants, C sub 1 and C sub 2. So I use the hybrid model, okay, in order to compute the heat distribution. When I apply the hybrid model, okay, I use the information from the experimental data, then I was able to get this constant C sub 1 and C sub 2. Okay, then once I obtain the corresponding expression for the heat flux for this propane torch, this model, then I use this heat input into the simulation and compute, okay, the problem. When I perform the numerical calculation, you can see here the result, no? The result of the experimental versus numerical data. You can see on the continuous line is the experimental data, and that line is the numerical data. And you can see, as I mentioned before, no, this process lasts only 30 seconds. 30 seconds. This is for 10 seconds. You can see the experimental and numerical data. This is 20 seconds. So you can see it's not exactly the same. So there is an error, but we can say that the overall, this numerical method agree well with the experimental data. Once we verify this agreement with experimental data, we continue with the simulation, okay? In this analysis, in order to get a three-dimensional result, because the client or the person was interested in the three-dimensional. So, but we perform a two-dimensional. The question is how to create or approximate a three-dimensional. What we did here is because we have a heat flux in terms of Z and Y, we model half of the flat plate. We cut different planes, okay, in this direction, and we model different planes individually, and then we couple all this model and integrate in a single one, no, in order to obtain, we call this a quasi three-dimensional model. You can see here, this is when you this is the slides, you cut the heat pipe into different planes. You can see how is the behavior of the temperature. This color, this is the near to the center, no? This is far away. This is far away from the center, but this is the near to the center. It's only half for the heat pipe. So what happened if you analyze the heat input, but for a solid plate. And you can see, for a solid plate, there is a dramatic, significant hot spot temperature in the core because this is solid material. But for the heat pipe, you can see, thanks to the vaporization and condensation, you were able to keep almost a uniform temperature within the heat pipe. And here, you can see here, this is the heat input. So you can see how is the temperature. This is in the back panel. You can see how the temperature on the back panel change. If you are using a solid plate, aluminum plate. If you're using a flat heat pipe for transient operation, you can see here that how T for these two geometries have the same dimension, only, but here this is the heat pipe, and you can see the concept. For the same heat input, you can see the temperature here. On this side, this is the heat input, the heat inside, this is the color side. You can see here in this point how T, is almost uniform for the heat pipe. So that's the idea, that the heat pipe provide almost a uniform temperature distribution of the system. That's good. Also, when I apply the quasi three-dimensional model, as I mentioned before, I cut the plane into different slides, several slides, and model individually separately, and then I couple all the simulation, and then I was able to solve, with some limitation, the three-dimensional output, that is the surface temperature on the heat pipe. You can see this is at 10 seconds, 20 seconds, 30 seconds, and this is 40 seconds. You can see that temperature here. So then, in order to validate this model, also we compare with experimental data. So this is numerical data, and then we compare versus experimental data. And you can see here in this experimental data, there is a almost similar response. Here they use different color because this is a thermal infrared camera. But if you check the reading, this is 400. Is almost so when we compare, we obtain basically almost a similar temperature distribution using the heat pipe simulation. As a concluding remark, I can say that the thermal analysis or the thermal model was important, a critical step, that allow us to determine the main dimensions of the heat pipe. Also, the thermodynamic analysis or thermal model allow to optimize the size of the weakness, the size of the heat pipe in terms of the heat inputs. So in order to achieve this result, we assume a thermal equilibrium. Although the actual process is not in thermal equilibrium, but by making the assumption, it was possible to get some the dimension of the heat pipe. Also, by the thermodynamic analysis, we notice that this heat pipe can work as a heat capacitor for thermal storage. So this a heat pipe is well designed for transient operation, but at the same time, it can work as a heat capacitor. So means that the heat pipe can store significant amount of energy and still operate under a fixed temperature, that you cannot exceed the temperature, as I mentioned before, 300 Celsius. So, as concluding remark, also we can say that a complete mathematical model and fluid flow was developed to evaluate the effects of non-uniform, also a transient heat process for this complex system. So We apply the explicit finite difference model in combination with a control volume model to discretize the governing equation, no? The momentum equation, the continuity equation, okay, and the Navier-Stokes equation. So also in this study, we were able to model the non-uniform heat flux distribution applied by a propane torch, no? By applying the hybrid method. So this model was successful because we compared with experimental data, we got a good results. So finally, I can say that the experimental data was in good agreement with numerical data. So also we can conclude that the temperature on the back side, on the cool side of the heat pipe was almost uniform. Okay, so that's was good because that is the idea, no, of having a heat pipe as a thermal spreader that you can have an even heat transfer distribution on the system. So this is the most important concluding remark about this study. Also, this model was applied later to one colleague from University of South Carolina. Also, we collaborate with this code. Also, one PhD student used some of this work, no, to do his study. So with this concluding remark, I conclude my presentation. Thank you very much for attending this long presentation, 1 hour. Let me know if you have any questions. Thank you very much.
The session is open for any discussion.
Yes, I think yes, you have. Yeah, I still have some minutes for that.
Participants, if you have any questions, you are free to ask, please.
Hello, Dr. Carvajal.
Yes,
this is open. Just
hey,
to
Doctor.
just to say hello. That's all. That's all. Just to say. Yeah, we'll meet later. Okay.
Thank you, Dr.
Now I invite Dr. Jensen Joseph, Associate Professor, Department of Mechanical Engineering, ICCME School of Engineering and Technology, to propose a vote of thanks.
Thank you, Sanju sir. I think I'm audible.
Yes, sir, you are.
Yeah. I thank Dr. Giordo Carbajal for a knowledgeable keynote address, which is very much apt for this conference. Right from the inaugural address, your session gave a deep insight into computer simulation and its extended application in heat transfer. And many of our final year students are here. Definitely this session will be helpful in their future career. Also, many of the researchers are here, and this will be helpful in their research path. On behalf of Mechanical Engineering Department, ICCME School of Engineering and Technology, I thank Dr. Gerardo Carbajal for delivering a wonderful keynote address. Thank you, sir. And I thank all the participants, the colleague, and all my dear students for patiently listening to this session. And thank you all. Thank you.
Thank you.
Thank you, Dr. Jensen Joseph. Ladies and gentlemen, now we have a short break of 5 minutes. Before we disconnect to reconnect, let me kindly request you to fill in the feedback through the link posted in the chat. Thank you.
Thank you.
Thank you, sir.
Thank you. Yeah, we have internal communication. No, it was nice to meet you via Zoom. Yeah.
Yes, sir. Yes, sir.
Thank you.
Thank you, sir. Thank you. Thank you.
Thank you.
Hello, sir. Sir, Shobhan, sir.
Hello.
Hello, sir.
Ah.
Sir, we will make you the co-host right now, and you can try the presentation if you require.
Okay.
Okay, sir. Thank you. Yes, sir. Sir, you are already the co-host, sir. Sir, would you like to try presenting?
Yeah.
Vishnu, sir, please stop the presentation.
Where shall I?
Sir, at the bottom on the panel, you can see a green icon.
Yeah,
we have the share. Yes, sir. Yes, sir. Yes.
There I have to click. Is it?
Yes.
Then
you can select either screen share or window share. You can just open your PPT.
I've opened it already.
Then maybe the share screen, sir. The entire screen, or maybe the window, as you like it.
One participant can share at a time. That's where I have to click.
Multiple.
Okay.
Yes.
I click there. Okay. Multiple participants can share simultaneously.
Yes.
There I have to click. Is it?
Yes, sir. Yes.
Okay, I've clicked, but nothing has happened.
So once again, can you try again share screen? And
yeah,
when you click the share screen, there will be some windows coming in.
Yes.
Click on the window which you want to share, and then click the share button, which is on the right hand corner, bottom corner.
Okay.
Yes, sir. We can see that.
Just come up now. Okay.
Yeah.
Okay, fine.
Yes. Sir.
Okay.
Good, sir. Thank you.
No, I have to put it in the other mode.
Full screen. Full screen F. Yeah.
Where do I get it from?
Sir, you can just press F5 or
F5. Has it come to full screen now?
No, sir. It is still the normal mode.
So how do you otherwise?
Otherwise, maybe in the file option, you can start slide sharing. Vishnu, sir, can you please help?
Yeah, in the file option.
Full screen mode. F5 വന്നില്ല.
അത് വന്നില്ല, അത് വരുന്നില്ല. Probably different computers ചിലപ്പോൾ വ്യത്യാസമുണ്ട്. Share.
Sir, ഇവിടെ
has it come to full screen?
No, still we can see that on the left side there is a panel of.
Okay.
Sir, sir, ഇപ്പോ ഒന്ന് F5 അടിച്ചു നോക്കോ ഒന്നും കൂടെ.
Yes.
Yes.
Just gone to full screen. Okay.
Yes, sir. Yes.
Now you just have to present.
Yes.
Okay.
Good, sir. Thank you, sir. Sir, shall we start, sir? It's already 11.
Yeah, we can.
I'll announce and we'll start.
Can you see me?
Yes, sir, we can see.
Good morning, sir.
Good morning. Yeah.
Ladies and gentlemen, we are moving on to our second keynote session. I would like to invite Dr. Ragaral, convener, ICCME 2021, professor and head of the Department of Mechanical Engineering, ICCME School of Engineering and Technology, to welcome the keynote speaker.
Am I audible?
Yes, you are, sir.
Oh, thank you. Respected keynote speaker, Professor Dr. C.B. Shobhan, other distinguished guests, and dear participants. It's my great privilege to introduce and welcome Dr. C.B. Shobhan, who is a great researcher and gifted teacher in the field of engineering and technology. Dr. C.B. Shobhan teaches in the School of Material Science and Engineering and in the Department of Mechanical Engineering, National Institute of Technology, Calicut. He is also a research collaborator and affiliate at the George W. Woodruff School of Mechanical Engineering, Georgia Institute of Technology, USA. Dr. Shobhan earned his PhD from Indian Institute of Technology, Madras in 1990, following his Master's of Technology from the same institute and Bachelor of Technology from Regional Engineering College, Calicut, which is presently National Institute of Technology, Calicut. He performed postdoctoral studies at Purdue University, Indiana, USA in 1999 to 2000. And since then, is focusing on research in microscale and nanoscale heat transfer. Dr. Shobhan was visiting faculty member at Rensselaer Polytechnic Institute, Troy, New York, USA during 2003-2004, working in the area of microscale heat transfer. He has also held research positions at Nanyang Technological University, Singapore, and the University of Wisconsin, USA. At the international level, Dr. Shobhan performs collaborative research with Professor G.P. Peterson, former president of Georgia Institute of Technology. He has been a visiting researcher at Georgia Tech since 2010. I was indeed fortunate to have Professor Shobhan as my research supervisor. Out of his busy schedule, he agreed to be part of our conference. On behalf of ICCME 21, from the bottom of my heart, I extend a warm welcome to you, sir. Also welcome all the dignitaries and participants to this virtual gathering. Thank you.
Thank you, Rag. I hope we can start my presentation. I hope all of you can hear me. Rag, can you hear me?
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
Okay. Now, I'll be talking in the next 45 minutes to 1 hour on some small but interesting computational studies on fluid flow and heat transfer applied to small channels. Small channels, when I say, they could be of different sizes, but all the dimensions are very small. So they may fall under the category of micro channels or mini channels or dimensions of that sort. And so we generally call them small channels. These channels having very small cross-sectional dimensions. So this study is a part of a much larger study which contained computational studies and experimental studies on fluid flow and heat transfer in channels, in which I am just concentrating on computational studies that we have performed on fluid flow and heat transfer in these small channels. So this part of this was taken up as a PhD research by a research scholar in our department sometime ago. So let us proceed to the things that I would like to talk to you in this presentation. I will first start with a brief introduction of these channels, these small channels, and background of its use, where it is used and what kind of applications will lead to the use of such small channels. And I will just talk a little bit about micro and mini channels and their classification. Then I'll come to the channel configuration and formulation of the channel that we are going to discuss in this lecture. Then we'll come to typical computational results for channels. So here I will first start smooth channels with our basically what we usually do in analysis of channels is by not considering any variations in the surface profiles, that is assuming only smooth channels. So we'll first try with typical computational results, studies and computational results for the smooth channels. Then I will come to some interesting aspects on the walls of the channels, namely cross-sectional irregularities. Cross-sectional irregularities in the channels, and how do we extend this computational studies for smooth channels to channels with the cross-sectional irregularities. So the computational approach. Then we'll just talk about some computational results for compact passages and mini channels also. Then we'll come to some experimental channels and some comparison of results with experimental results for these channels. Then I'll briefly talk about micro milled channels and their computation studies on finding basically the heat transfer and fluid flow in these micro milled channels. And let us come to conclude the session by some concluding remarks. This will be the general way I will deal with this presentation. So let us start our discussion about convection flow, convective flow of liquids in these small channels. So we say that convective flow of liquid in mini and micro channels. This is a promising technology. We always talk about the micro channel flows and mini channel flows, and or rather the flows through these small channels to take away especially the heat transfer, take away the heat that is generated in electronic components. So these channels, these small channels, like the mini and micro channels, is a promising technology for effective heat dissipation from these electronic components, especially electronic components, and various other devices. Experimental results, we many times do experiments on these small channels to find out how the heat dissipation takes place and correlate them to find out correlations which can be used in design. But experimental results are often found to differ compared to the theoretical results of the apparent regular geometry, basically because of this term itself. The apparent geometry is what we use for normally for computational studies. Apparent means regular geometry. We just take the geometry to be exactly square or exactly rectangular. So we do not talk about the surface variations in the channel surfaces in doing our computational studies. So we do computational studies using the apparent regular geometry of the channels, but it's always found that when we compare with real channels, the experimental results of real channels, this many times varies. These are many times different from the apparent regular geometry of channels. So it is desirable to develop a strategy to incorporate the actual sectional irregularity on the computational domain. So that we do not do always, because it's not very easy to do the actual surface geometry in the computational domain, because the cross-sectional geometry may be such that if you look carefully at the surfaces, the geometry will not be straight or not have any definite shape. The channel surfaces will be so much different from the regular shapes that we always consider for our computational studies. But it is always desirable to have, as far as possible, the cross-sectional geometry or the cross-sectional irregularity of the channels also taken into consideration on the computational domain of the channels. So I will come more to the cross-sectional geometries later. So this method of incorporating the channels or incorporating the geometries of the channels, the real geometries of the channel as far as possible on the computational domain. This should help to obtain the flow and heat transfer behavior more accurately in the channels, apart from the regular channels that we consider for studies. It's always better to have the actual cross-sectional geometries of channels as far as possible incorporated in the domain, and the computations done on these channels with this regular geometries. So this helps to obtain the flow and heat transfer behavior more accurately in channels of small cross-section, compact, mini, meso, and micro channels with realistic surfaces using a numerical method. So as far as possible, while using a numerical method, it may be always better to use geometries of the channel which are not apparent regular geometries, but as far as possible, the realistic geometry of the surface of the channel or the cross-sectional irregularities on the channels. If you can incorporate that as much as possible in the computation, that will be always better. So this with these goals, we are going forward to our computational work, computational study, which I will be which I'll be presenting now in a few minutes. So the background of the work basically is that comparisons are often made between experimental results and theoretical results on channels with apparent geometry. The regular geometry is always many times considered in making comparisons between experimental results and theoretical results. The experimental channels used are realistic channels, and the theoretical results many times are on apparent regular geometry of the channels. Now, how do the computational results using actual irregular geometry compare with experimental? This is one important aspect that we may like to find out when we are dealing with channels. How do computational results using actual geometry compare with experimental results? So the problem there is how to use the actual geometry, how to discretize this, and use the computational methods in order to find the regular geometry, the actual geometry results, irregular geometry results, and compare them with experimental results. So the computational results using actual irregular geometry. This is one of the major goals of going for this type of computational studies, as I'm going to present before. So the computational results using actual irregular geometry, how does it compare with experimental results? Now, the actual remains are incorporated in computational analysis. This is how it is done. In the computational analysis that we develop for flow and heat transfer in channels, we normally use the regular channels, but here the actual domains are incorporated in the computational analysis by something called a boundary tracing technique, by which the actual computational geometry of the channels is incorporated in the computational analysis, and the computation is performed in order to get the results and compare it with the regular geometries. This is what basically will be the study. This will be the basically the method of approach of this study that I'll be presenting before you. So when we look at micro and mini channels, micro and mini channels, as you know, they are channels with very small cross section, and cooling fluid is forced through the channels built-in substrate attached to an electronic device to take away the heat generated. This may be a usual method of the micro channels. So the cooling fluid is forced through the channels built in a substrate attached to an electronic device to take away the heat generated. That is the basic method of using the channels and the fluid passing through the channels. The heat dissipation capability of micro channel heat sinks has been found to be very high due to large surface areas available per unit volume. So there has been a lot of discussions, and it is nothing new. The use of micro channel heat sinks and mini channel heat sinks for heat dissipation from through the channels, the fluid flowing through the channels, and the heat dissipation capability of micro channel heat sinks has been found to be very high due to the large surface areas available per unit volume in micro channel arrays. Now, mini channels, as you know, mini channels are also small channels. They are channels of hydraulic diameter in the order of millimeter. So micro channels are very small, much smaller than mini channels, but mini channels are also classified as small channels having the hydraulic diameters of the order of millimeter. And convection cooling in mini and micro channels is a promising technology for effective heat dissipation from electronic components that you know, convection or liquid cooling in mini and micro channels. So I've shown a photograph of a chip here, which is attached to which a channel is attached. You can see the openings of the channel, the openings of the channel, the inlet and outlet of the channel on the left hand photograph. And the right hand, I've seen a schematic, I've shown a schematic diagram of a channel array. It's an embedded channel array within an area where you have small channels fabricated and you have an inlet and outlet of the channel. So this kind of a channel may be the one which is seen attached on the left hand figure. Now, the effect of surface irregularities, as I was telling just now, the effect of surface irregularities is prominent in small channels. So I have a couple of photographs here. One is an apparently rectangular channel, a micro channel, rectangular in shape on the left side, but it is not really rectangular. If you actually see the surface of the channel, the actual shape of the channel is not rectangular. So basically, the variations in the surface is prominent. When the channel becomes smaller and smaller, the surface irregularities become more. It becomes more dominated in the channels. The second one, the circular channel. Here also, the surface irregularities become important, and they become different from the actual the shape of the surface as we take for a computation. In the computation, we take it as a circular channel. The second one, the circular channel, but really it is not a circular channel. When you come to the real shape of the channel, the surface irregularities also play a role in the formation of the shape of the channel. So the two channels, the first one, the rectangular channel, and the circular cross-section channel, they are not really rectangles or circles in shape. So when we deal with very small channels, we always have to think more about this, and we have to take it as close as possible to the realistic shape of the channel as far as possible to do the computational studies of fluid flow and heat transfer to the channels. The effect of surface irregularities is prominent in small channels. So the size of the channels becomes smaller and smaller. The shape of the irregularities or the shape difference from the actual shape is different from the apparent shape. So in the first channel, for example, even if we call it a rectangular channel, the actual shape is not rectangular. The second one, even if we call it circular channel, it is not really circular. So incorporation of the real channel geometry as far as possible in the computational domain will give better results. Definitely, if possible, we try to incorporate the real geometry of the channel as far as possible into the computational domain for doing the computation. So when we look at the channel classification and the classification based on the size or the equivalent diameters of the channels can be basically classified into these. The two groups of channel classifications were proposed by Kandlikar et al. 2006, and Mehendale et al. Had given again a group of classification before Kandlikar. So during the time 2000 to 2006, people were practically working on these channels and in naming the channels and using methods for computation and experimental studies on these small channels. So according to Kandlikar, conventional channels are channels which are greater than 3 millimeter in equivalent diameter, and below that various channels were named based on the equivalent diameters of the channels as mini channels, micro channels, transitional micro channels, transitional nano channels, and nano channels. So for these different dimensions of the channels. And Mehendale's classification were also like this: micro channels, meso channels, and compact passages and conventional passages. So these are the basic classifications which are applied to in naming the channels as micro channels or mini channels or transitional channels or nano channels in the literature. Now let us come to the channel configuration. The channel configuration and formulation for a regular cross-section. Let us start with a regular cross-section channel and later come to a channels with irregular cross-section. So the regular cross-section basically is a rectangular channel. So this is the, so for example, this is the total channel array with the 5 channels in them, and one of the channels is taken and the channel is separated, and this right hand side, this black portion is the metallic portion. So we have on the right side, I have shown the larger view of the channel where we have the channel inside. Inside we have the channel, and outside you have the metallic portion. So this blackened portion is this represents the channel. The inside portion is the channel section, half of the section, and the outer portion is the rectangular array, rectangle of the metal outside the channel. So this right hand figure shows the channel section and the outside surface of the channel. So this section, if we analyze, can give the complete picture of what is happening in one of the channels, because half of this region will be representative of the complete channel. The physical model of the miniature channel arrangement is shown here with all the dimensions W and WT and height HC and H, everything marked here. So we come to the formulation of the equations governing to the fluid flow and heat transfer in the channels. I'm not discussing very deeply into it, but let us understand that basically the equations that can be used to the equations which are used here are the momentum equation, which shows about the velocity. So the first equation is the momentum equation, and the pressure equation dp by dx equal to dp by dy. And with all these different non-dimensional variables, as I listed here, x, y, and capital U, non-dimensional variables, and bulk mean velocity definition. These equations can be finally written in this non-dimensional form. This is the non-dimensional momentum equation that is used, where U star is given by V star. So let us not worry more about this. So we have the non-dimensional form of the velocity equation for a two-dimensional flow. So this is the two-dimensional flow equation with U star given as the non-dimensional velocity given by this expression. U star is equal to hz by this expression given by U star is equal to uz divided by these terms hc star by mu into dp by ds negative. Now, subject to U star equal to 0 for all the boundaries of the channel cross section, because the velocities are 0 on the boundaries of the channel cross section. This can be written as U star is equal to 2 by W by HC into this expression given here. So this U star can be derived as this expression that is given at the last row of the page. So U bar star is equal to 2 by W by HC into this step. So that can be applied here as U star. So U bar star is given here, and U star is equal to U star by UZ is equal to U star by U bar star, and this equation can be written in terms of U star. So U star dou square U star by dou x square plus dou square U star by dou y square is equal to -1 is a governing equation. That is the momentum governing equation for the channel, where U star is given by this expression. U star is equal to the velocity divided by this term. So now energy equation also can be written in the same non-dimensional form. The energy equation, the steady state energy equation, also can be written as shown here, neglecting viscous dissipation. This is the first equation is the energy equation, and for the substrate, the two-dimensional conduction equation is also given. So this is for the fluid. First is the energy equation for the fluid, and second one is the conduction equation, which is again the energy equation for the two-dimensional conduction in the substrate. So non-dimensional, this also can be non-dimensionalized with non-dimensional terms. Given here, theta is given by this. Theta is equal to kf by qw into t minus db, and dp by ds is given by this expression qw divided by this, etc. This equation. So the two equations given here at the below bottom of the page can be used in order to be substituted in the energy equation to write down the two energy equations. So the steady state energy equation for the laminar fully developed flow can be written as the first one in the fluid, and the second one is the flow in the substrate, that is the conduction equation or the energy equation in the substrate. So I have shown all the equations. So the fluid flow equations and the energy equation, the fluid flow velocity equations and the energy equations derived in this non-dimensional form from the two basic equations. So now look at the computational analysis that we'll have to apply. This is the computational analysis as I was shown before. This is half the channel, and we have written all the equations here. So d theta by dy, d theta by dx equal to 0. This is for a regular geometry domain that we have taken the equations. This is for the regular geometry that all the equations have been written on this geometry as shown in the diagram for the computational analysis. So that is for the regular geometry of analysis. And when we solve the equations, later I'll tell you what are the basic consideration in getting the solution of the equation. So the regular cross-section channel will give you these kind of profiles. The non-dimensional velocity given on the left-hand side, distribution of the non-dimensional velocity for the entire channel cross-section, and for the non-dimensional temperature for half the channel cross-section, as I've shown the half the channel cross-section. So these will be the two profiles, typical profiles. So this is for a typical channel for 4 by 4 millimeter dimension used. So the channel with dimension 4 by 4 millimeter by 4 millimeter on the wall has been analyzed using the equations that non-dimensional equations that I have shown before, and the equations were solved to give these equations to these profiles for the velocities. So for other channel dimensions also, these profiles, these velocities and temperatures can be solved by using the equation. So this is for the regular cross-section of the channel. But actually in cross-sectional, if you look at the cross-sections of the channel, as I was telling before, they are not at all regular. So the various channels which we apparently call rectangular channels in the actual case, in the actual way, the channels look like this. They are not regular. They are not square channels or rectangular channels. But when the channels are fabricated, the cross sections, because they are very small. These channels are very small, of a few millimeters or even lower. So this is only 550 microns by 50 micro channel. This is supposed to be a rectangular channel, but you know, while fabricating, the channel is actually formed in this particular form. So basically, when the channels are formed, they are not rectangular. But if these channels become part of a large domain, okay, these channels will be small, and it may be fair to even to use rectangular cross section. But when you are using these channels are part of a very small domain, these channel cross sections are also important. And if you take these channel cross sections are rectangular and do the computational work, the computational results may not match with the actual channel or the realistic problem. So basically, we'll have to, as far as possible, incorporate the non-rectangular shapes of the channels in this. For example, the 4 channels shown here, they cannot be dealt as rectangular channels because their dimensions are such that when the channels are formed, the channels are non-rectangular, and the shape has to be incorporated as far as possible correctly into the domain of analysis. These are another 4 channels here. The channel shape is very arbitrary. This is not a real rectangular shape. This shape deviates from the rectangular shape, even though we may call it a rectangular channel. They are not rectangular channel. This is not a rectangular channel. The second one is also not a. So all the 4 channels are rectangular channels if we generally call them, but when we look under a microscope, the variations are like this, and the channel sides are not straight, and the channels are not rectangular channels. Now, when we deal with these non-rectangular channels, also, we can use the same kind of formulation, but only thing is that the side walls have to be appropriately taken, and the side walls, in the side walls, the rectangular, non-rectangular cross section has to be incorporated into the side walls, so that the non-rectangular, non-straight cross sections can be taken into account in the analysis. So the method which I am going to deal with here is the Gauss-Seidel method, line by line method only. And the grid selection is unequal grids. Later we'll see how the rectangular cross section can be accommodated by taking unequal grids for the grid domain of the channel. So a grid independent study was also done for four-side metal rectangular channel, irregular channels also, and the grid size were taken, Nusselt number was calculated, and the convergence of the grid size, so the smallest grid size which can be used for the channels was chosen by a grid independent study. Now let us look at the schematic diagram of the actual surfaces. On the left, you can see a typical cross section of a realistic channel. So this realistic channel cross section, sometimes in actual and computational study, we may take it as a rectangular channel. But in these small channels, this can never be taken as a rectangular channel because the sides are all different. They are not at all rectangular. So the grids also has to be accommodated for this shape of the channel as shown in the diagram. So this channel, the grids have to be uneven, unequal. The grid selection in the computational domain has to be appropriately taken so that the channels can be, when discretized, as far as possible, the channels can be discretized as I have shown in the diagram, with as many grids taking care of the irregularities of cross section of the channel. So the channels on the general grids are rectangular, as you can see, but near the channel walls, the grids have to be taken closer. So unequal size of the grids at the channels as far as possible, as close as possible, so as to involve grid points on the channels as far as possible on the real cross-sectional geometry of the channel. So everywhere, as far as possible on the grids, on the channel surfaces, the grids are accommodated very closely so that the grid division can take as many points on the channel surface as possible, as shown in the diagram. So surface profile can be used for a realistic channel surface for the channel surface, as I've shown. So the surface profile for a realistic channel, typical actual channel surface, the surface profile may be like this. So these type of surfaces are taken on the sides of the channel, and the grids are taken closer so that the channel can be discretized at this variable in this variable shape. So the realistic surface profile with appropriate curve fitting, which shows the curve which shows about the approximates the realistic surface is shown here in the red, but the actual surface profile is as shown by the blue line on the diagram. Now, details of the baseline case analyzed I've shown here. I'll be showing one of the cases. The parameters, geometric dimensions, flow rate, and for experiments, the fluid inlet temperature. These quantities are chosen. Parameters, values in the baseline case are chosen here, and the thermophysical properties of silicon, aluminum. We have analyzed channels with two different materials, silicon and aluminum channels, and water as a working fluid inside the channel. So the thermal conductivity, density, and kinematic viscosity of the materials and the kinematic viscosity of water are chosen as shown in the table. Now, aluminum channel with irregular cross-section. So, formerly, you remember that I've shown the result of aluminum channel with regular cross-section. So here it's with accommodation of the side profiles as I've shown for the channel. So unequal grids are taken on the sides of the channel. So on these lines, these sides of the channel, the grids are taken unequally. That is, unequal size is obtained by getting the actual profile of the channel and dividing the profile into unequal grid sizes, and the unequal grids are taken on the surfaces of the channel, and the two diagrams shown here. One is a distribution of non-dimensional velocity for the entire channel cross-section for the unequal grid size channel or the irregular cross-section channel. Second one is the corresponding temperature distribution for the unequal, the entire channel for this channel sides with unequal grid sizes used or irregular shapes on the sides of the channel. So basically the channels which are used here, the actual cross-section as far as possible with irregular cross-sectional dimensions are used. Comparison of results for channels having irregularities on all four sides. If you compare like this, the analytical results are given here, and the numerical solution for smooth channels. Smooth channels are regular channels, as I was shown in the beginning. The regular channels, the hydraulic diameter, the CF into RE value, and the Nusselt number value are obtained as this, whereas for irregular channel, we can see the differences in the values from the numerical solution for the smooth channel and the irregular channel. The two channels vary between each other. This is because of the irregularities of the shape used in the computational domain. So comparing with the analytical solution, the numerical irregular channels definitely will have a slightly different values of hydraulic diameter and Nusselt number when compared to the analytical solution and solution for the smooth regular channels. Now, let us look at some more analysis. Compact passages. So compact passages are, so basically this is the methodology that I've used, applied for all different kinds of channels, different sizes of channels, which we can call by different names. The compact passages normally are passages with the hydraulic diameter 1 to 6 millimeter, as given by Mehendale et al. And this hydraulic diameter is 1.1 to 6 millimeter is called compact passages. So the computation approach gives two-dimensional analysis, Gauss-Seidel line by line iterative method for the analysis, unequal grid selection as I've shown along the sides of the channels, so that as far as possible the channel can be discretized as much as possible, and channel walls can be taken into the domain of analysis. So unequal grid selection on the channels, and actual surface profiles were measured by surface profilometer and incorporated in the computation domain. So the actual profiles were measured by the instrument called surface profilometer, and these surfaces were incorporated in the computation domain. So basically, the solution interior of the channel will have the same equations to be solved, whereas all the equations are the same, but the boundary conditions will always be applied to the realistic boundary of the channel, which is given on the sides of the channel by where the unequal grids can be applied. So some typical results of this computation are shown here. CF into RE results here. CF into RE has less than regular geometry. Variation of CFRE due to effect of CFRE is varying due to the effect of CF, and other CF variation with respect to volume flow rate and pressure drop variation with respect to the volume flow rate of the channel. So basically, the same channel flow analysis has been applied to these channels with irregular geometry. So basically, the channels are taken with the irregular geometry, wall geometry, where the discretion is done so that the nodes are in the irregular geometry, and the channel can be discretized on the walls where the irregular geometry appears based on this this discretization process. So the typical results again on Nusselt number and aspect ratio of the channels is also shown here. Nusselt number greater than regular geometry of the channel. So we have shown the graphs were analytical results by Case et al., numerical regular channels, and numerical side rough channel, where the actual geometry has been incorporated in the computation. Now, some results, maximum deviation of CFRE, CFRE variation with respect to aspect ratio of the channel, width by height of the channel, and Nusselt number also with respect to aspect ratio of the channel. So these are heat transfer results, which may not be that interesting for people from other branches, other streams of the subject, but please understand that the fluid flow and heat transfer results can be calculated by this methodology by applying the real channel cross-sectional area on the side walls of the channel. Now, mini channel analysis, just like micro channel analysis, hydraulic diametation, the ratio 200 microns to 3 millimeter. These are called mini channels, and 2 by 2 mm channel, the variations of CF into RE with respect to aspect ratio is given in this first diagram, and Nusselt number with respect to aspect ratio is shown in the second. So here the variation of flow and heat transfer parameters with aspect ratio greatly depends on the cross-sectional geometry this found. So the cross-sectional geometry, that is the most important point that I would like to stress here, that the cross-sectional geometry of the channel can be incorporated in the computation as far as possible in a better way than taking the regular cross-section channel. So by taking the real cross-section of the channel and appropriately merging the nodes of the computational domain with the real cross-section of the channel, we have found the real cross-section of the channel and incorporated that in the computation. Use pressure drop variation in the channels. Second one is the pressure drop versus number of irregular sides of the channel. Pressure drop is found to be increased in the channel irregularity on the side. So as you know, the channels, even though it is peripherally a rectangular channel, is taken as an irregular channel, and the real pressure drop associated with the irregular shape of the channel is found out by using the computational method. Now we'll get an analysis of channels with actual surfaces, actual surface geometry, experimental channels, in order to compare or in order to see whether the correctness of the theoretical results that we have obtained. So the actual surface geometry, the actual channels were fabricated, and this is how the experimental channel assembly was fabricated in the particular form with optical glass and aluminum plate. With the experimental channel is fabricated in this particular form, as you have shown. There are various, that's an experimental work that you have done. I'm not going to explain more about the experimental work, but please understand that the test section channel was fabricated like this with optical glass cover on one side, so that we can see inside the channel, and we used interferometric measurement called by the method called Mach-Zehnder interferometry in order to measure the heat transfer and temperature distributions in the temperature distributions and heat transfer in the channel. So I'm not going to explain the Mach-Zehnder interferometric setup here, but this method can be very effectively used in order to get, this is the Mach-Zehnder interferometric setup, photograph of the Mach-Zehnder interferometric setup, which you have used to find the real channel cross-section. Look at the real channel cross-section, and the interference patterns of the channel cross-section were taken. And by taking the fringe patterns of the cross-section, by taking the fringe patterns and analyzing the fringe patterns, we can actually find the temperature distribution along the channels. So this has been made for this type of analysis has been done, taken the photographs of different polished surfaces, medium rough surfaces, maximum rough surfaces, and the surface variations of the fringe patterns have been found out. So actually it is found out by the distance between the fringes in the cross section, and it can be measured by microscopic measurement, and actually the different fringe patterns can give different values of heat transfer along the surface. Now basically the profiles of the channels, as I've shown, three different examples of the profile of the channel, where irregular the profiles of the channels, the channel surface otherwise which would have been taken as a straight surface, they are actually forming profiles like this, and the channel walls are not straight, and channel walls are of these particular different forms because of the they are fabricated. These small channels are fabricated. The channel profiles are always having the variations as shown in the diagram, which are away from straight surfaces. So the computational results of apparent geometry, that's apparent geometry. Apparent geometry is a straight channel. So the computational results of the straight channels, distribution of the non-dimensional velocity on the left side and distribution of non-dimensional temperature on the right side are shown, whereas the computational results incorporating the actual geometry, it is shown on the left and right, which are different from the computational results for the straight geometry. So when we compare the experimental and numerical results, the experimental results have shown 0.008 as the hydraulic diameter, and that's measured the experimental hydraulic diameter, which is the irregular channel. We have got correct 0.0008 for the irregular channel, whereas for the numerical work for the smooth channel, it is much different. So the CFRE values are also different, and the Nusselt number values are also different, and the irregular channels are the results are much close or very close to that of the experimental channels. So the analytical results from Osthusian has been compared with numerical smooth channels and numerical irregular channels, where we find out that the analytical results are close to the smooth channel geometry by Osthusian, but the actual numerical irregular channels that we have used with the irregularities also imposed to the channel is different from the Osthusian results. And we already found that these results are much close to the experimental results. Now, as the last portion, I would also talk about micro milled channels. So these micro milled channels are fabricated on aluminum substrate, aluminum or other substrates, but we have used aluminum substrate by micro milling process. So the channel hydraulic diameter in the range 300 to 1000 microns, and the actual geometry is obtained by a microscope. The actual geometry, the side profiles, as I have shown in the diagrams, have been obtained by a microscope, and MATLAB program is used to get the boundary profile quantified. So after obtaining the geometry by the microscope, it is put in the MATLAB program so that the boundary profile can be quantified, and the actual geometry is incorporated in the computational domain. So the actual geometry of the side walls has been measured by the microscope and quantified by the MATLAB program and incorporated in the computational domain. So these are the geometries of the channels that we have studied. The two channels are shown here, 500 to 500 micrometers. These small geometries has been measured and quantified using the MATLAB program. And this is the flow chart for the calculations that I'm not explaining that. This is the flow chart for calculation in the MATLAB program for the geometry. So the micrograph, the micro channel cross section, for example, has been obtained by MATLAB program, where these values have been measured, the height, width of the channel, and top width of the channel is different from the bottom width, which shows that the channel is not regular cross-section channels. So this is the actual channel profile as we have obtained using our boundary tracing technique. This is the variation of the channel wall, and this channel wall is used for the computation. So actually the grids are arranged such that the grids fall on these channels, and similarly other channels, different channels of different dimensions and different sizes are shown here, where we have measured the sides of the channel, and boundaries are drawn, and the boundaries are drawn, and the grids are aligned to the boundaries of the channel in doing the computational analysis. This is another set of 3 channels. So you can see that in these small dimensions, even though we call a channel a rectangular channel, they are not really rectangular. They are much different from rectangular channels. And if you measure the actual size of the channels and incorporate that in the domain of analysis, that will always give you better results and more accurate results, as we have shown. Now, the typical distributions with regular cross-section, the 2 channels with regular cross-section are shown here. This velocity distribution is half the temperature distribution. And for the channels with irregular cross-section, the variations are like this, where the bottom variations at the wall, we can see they are much different from the regular cross-section channels. So the variation in Nusselt number also has been plotted. Larger deviations in Nusselt number, larger deviations in Nusselt number of smaller channel is due to the significant effect of irregularity. So the Nusselt number has been calculated and compared with that of the regular cross-section channels, and it is found that Nusselt numbers are much different with respect to aspect ratio. If you plot the Nusselt number is much different from the smooth channel for the rough channel. So here also 3-side rough, 2-side rough, 1-side rough, depending on how many rough sides are used for the channel. The Nusselt number values are different from the smooth channel. So these are some of the results, even though I have given the lecture very peripherally. I hope that I have made you kind of go through the method and understand to some extent what we have done here. So the effect of variation, concluding remarks, I would say, the effect of variation of cross-sectional geometry that is significant in fluid flow and heat transfer for small channels. So it is not always fair to take cross-sectional geometry to be without any variation in it. Regular cross-sectional geometry will not always give good results in the case of the small channels, because the channels we are trying to analyze here are very small, of the size of micro channels or mini channels. Variations of flow and heat transfer parameters in the regular cross-section channel depends on both irregularity of height and shape of cross-section. So this will affect the flow and heat transfer parameters when you do computational work, and compare with experimental work, you can see the difference. So as far as possible, try to incorporate the real cross-section geometry of the channels by using the method that I have shown. Investigations on meso channels were carried out. Deviations are observed in Nusselt number and CFRE values compared to the regular channel. So the real meso channels, the values were different when compared to the regular channels. Parametric study has been conducted on numerical analysis of micro-Engg channels using boundary tracing technique. Large variation of flow and heat transfer parameters is obtained in the smaller channel cross-section as a result of the analysis. The smaller the channel cross-section, the larger the variation, as we can obviously understand. Assuming regular geometry over-predicts the Nusselt number. This is what I have found from the analysis. Assuming, as usual, we take the regular geometry of the channel and make the analysis. This over-predicts the Nusselt number. So it's always better to use the real shape of the channel by the methods that I have shown here, and incorporate that in the computation domain in order to do the computation work. So with this, I come to the end of the presentation. I just wanted to give the very peripheral ideas about the presentation, about the method that I used, but the actual method resulted in a much larger amount of work by a research scholar, Binoy Devi, who was doing his PhD work with me, and the three papers came out of this part of the work shown here. So thank you very much for the kind listening, and that's all. Thank you.
Thank you, sir. The session is open for any discussion. You shall either unmute and talk, or the chat box is live so as to post your queries.
Hello, sir. Am I audible?
Yes, yes, you are.
Sir, I am Jaydevan from Automobile Department of SAM School of Engineering and Technology. Sir, I have a doubt in this computational analysis. If we are analyzing the fluid flow in laminar region, so how we can incorporate this surface roughness on the analysis? Whether we have to give or model the boundary as it is, or is it possible to give some average roughness value like?
Yeah, it is possible to give average roughness value. So basically, what I've done is I've taken the boundary of the surface as a realistic boundary as possible. Okay, the boundary is taken as realistic as possible by tracing the boundary and incorporating that in the domain of analysis. And the other things on the boundary has to be taken as the average values, as you have taught. Yeah.
So the boundary is created by considering this average value as average value of roughness in mind, right?
Yeah. Yes.
Or,
yes. It is.
Okay, so it is just like it's come as a sinusoidal curve or something like that.
Yeah,
when
it can be fit to a particular curve. That is what I showed.
Yeah, you have shown a polynomial.
Yeah.
But is it is it possible to fit it as a sinusoidal curve, and we can give that?
What I'm telling you, it is possible, but it's always better to fit it as close to the real surface as possible, because we know the real surface geometry by making the measurement, and we can fit the graph. That is why I've taken a polynomial with many terms. So as a, if you take a lower degree polynomial, of course, there will be various problems with that. So in the actual real sense, it is a straight line that we are fixing, is it not?
Yeah, yes, yeah.
So instead of that, the more and more realistic the polynomial is, the result will be better.
Okay, okay. So first we must know the profile of the surface,
Yes,
right?
it's always better to
we
know
have
the profile. That is why we made the measurement using the microscope.
So one more question is, sir, you have shown some classification of microchannels, mini channel, mesochannels, etc.
Yeah, yes.
Is it strictly followed in this analysis? Because many journals still they will tell microchannel as a one.
They are not strictly followed, but these are the most common methods of classifying. That's all we can say. But we cannot clearly say that it is exactly this 3 millimeter exactly says. So basically, this classification also has to deal with the real kind of fluid flow in the channels. So fluid flow does not depend just on the dimensions. Other things like smoothness of the channels and things like that are also important. So based on that only we can clearly say which is a mini channel, which is a microscope channel. But basically the general classification is as I was given. That's all.
Okay. So this I think this microchannel, if you take this Candlicker's approach, so this microchannel is defined where you can see some deviation from that conventional theory, right?
Yes.
That is what, yeah.
That is where that is how you classify.
Okay. So more than a 200 micrometer dimension, that is hydraulic diameter, we can say. So mini channels most probably follow the conventional theory, the Navier-Stokes equation,
more close,
all those
more
things.
close to that.
More close to that. Okay, great. Okay. Thank you, sir. Thank you.
Okay, fine.
Any more questions? I invite Dr. Vidya Chandran, Organizing Chair, ICCME 2021, and Associated Professor, Department of Mechanical Engineering, SCMS School of Engineering and Technology, to propose a word of thanks.
Thank you, Sanju sir. Thank you for the opportunity. Let me proceed to my duty. Respected Professor Dr. Shobhan sir, Professor Axel, other dignitaries, and dear participants. It is my privilege to thank one of the great professors of the Indian Academia, Dr. C.V. Shobhan, for being with us and elevating the prestige of ICCME 21. The keynote session, even though it revolved around the most complicated topic in mechanical engineering, computational heat transfer, Sir has taken pain and explained it in a very simple and interesting manner that even our undergraduate students participating here could understand and take benefit from it. Professor, it is indeed the privilege of the conference and the participants to have an academician like you with us, with wide research experience in various international universities and laboratories with us today. I, on behalf of the SCMS School of Engineering and Technology, express our sincere gratitude for taking time out of your busy schedule and delivering the keynote session. Thank you, sir.
Thank you very much. Thank you.
I also thank the participants and the faculty of SSCT for joining us and taking benefit from the session. Thank you. Thank you so much and wish you a good day.
Bye.
Ladies and gentlemen, we come to the end of the day one keynote sessions. Now we have the parallel technical sessions 1 commencing from 12:30 p.m. to 1:30 p.m. All the participants are requested to join the respective link received through your registered mail. From 1:30 p.m. to 1:45 p.m., we have the lunch break. I would also like to remind the program agenda in the afternoon. We have the plenary session after the lunch from 1:45 p.m. to 2:45 p.m. And from 2:45 p.m. to 3:30 p.m., we have the parallel technical sessions too, and Numeka workshops as well. Thank you.
Thank you.
So it gives us really this also kind of, jet lag problems, morning, afternoon. So everybody 24-hour conference. No?
Yes.
We have participants.
So I'm going to wait for your, let's say, to give me, let's say, the start.
In 2 minutes, we will start.
Yeah. I see that that we can even wait a little bit because I mean it's always normally when you are live in the conference, then this is just really on the human based interaction. Now we have to use digital interaction, so it's making us an additional challenge to pass the message through it. But obviously the message go much faster and to many more people.
Yes,
I
yes.
see already 72 participants present, so it's a great number of. I mean, we normally you cannot get these numbers when you are in a real room and conference.
The benefit of COVID.
The benefit of COVID, yeah, make us interacting with this way, like we are all together here, but we are finally really displaced.
And it's good that we were equipped before COVID to handle the situation with all the platforms ready.
Yeah. But anyhow, it's really a big, pleasure for me and honor to be here with all of you.
So we also do remember the days you were in the campus.
Remember?
Yeah,
Nice to hear that.
We hope once everything got normalized, you will be here in the campus one more time.
Yeah, that would be great. I mean, I would really like to, to do it once more. I don't know if the time will permit with all these happenings of the COVID and so, but that is for sure in my plans to come again to Kochi because it's always a nice place to be and to meet you all there.
Oh, that sounds great for us, sir. Thank you.
Maybe Vidya, I can ask you for a small help during the presentation because maybe that could be also the message to all the audience. I mean that to put some questions basically in chat and then we can pick up some on the end because how they come, maybe we can also be interrupted, but I think that that if you basically somehow collect the questions, then we would be more efficient in answering. So I think how we were talking, it will be a kind of 45 minutes presentation, 50-minute discussion. But as you see the number of questions, maybe we can then adapt it and we can maybe speed up some things and make the other things more, let's say, more explanatory.
Definitely. We can do that. We will open the chat box and announce that. Sanju sir, please take care of this.
Yes, the chat box is live.
And also please ask the participants whenever they get a question, they can put that in the chat box without waiting towards the end.
Yeah, without waiting, because in that way, basically, and then I ask you kindly to select, let's say, and to you know, if there are duplications or something. And finally, if we will not have time, we will surely, I mean, like to have all these questions to reply you maybe by email or, you know, in whatever mean it will be, you know, appropriate.
So shall we start?
I think we might start, no?
Yeah. Yes.
Yeah, good.
Sanju sir, over to you. Welcome.
Welcome. Thank you very much. I mean, so excited. I mean, and really, I mean, it's a big privilege to give you this talk, and it's going to be really a very special talk. I mean, myself, Dean Vucinic, I'm in Brussels currently, and my colleagues are in Osijek, and you are there in India, and we all can do that. So it's really great to present this to you. And I'm really, I mean, once more saying big thanks that we could do that. So let's start.
So now we have the honor to welcome you. The secret of success is to do the common things uncommonly well. Ladies and gentlemen, good afternoon to everyone present here. I welcome you all to the afternoon session of the first day of the International Conference on Computing in Mechanical Engineering 2021. As you may know, we have 3 agendas in the afternoon session: the plenary session, parallel technical sessions 2, and NUMECA workshop. Now, it's time for me to invite Dr. Rag RL, convener ICCME 2021, Professor and Head of the Department of Mechanical Engineering, ICCME School of Engineering and Technology, to invite our distinguished speakers for the plenary talk. Over to you, sir.
Thank you, Sanju sir. Am I audible?
Yes, sir, you are.
Respected Professor Dr. Dean Vucinic, other dignitaries, and dear participants. It gives me immense pleasure to introduce and welcome Professor Dr. Dean to the plenary session of ICCME 21. Professor Dean is a professor at the Brussels School of Governance at Vrije University, Brussels, which is an alliance between the Institute for European Studies and Vesalius College, which he joined in 2017 as adjunct professor in global business and entrepreneurship and master's preparatory programs. He is affiliated to BUB since 1988, and before joining, he was guest professor and senior research scientist at BUB Faculty Engineering Sciences in 2 departments, mechanical engineering and electronics and informatics. He is also visiting full professor at Faculty of Electrical Engineering, Computer Science and Information Technology, University of Osijek, and Technical Faculty, University of Pula, both in Croatia. His work is related to research and development projects, and his interests covers scientific visualization, modeling and simulation, optimization methodologies and techniques. His PhD became a book as in the early 90s. He developed a CFU computational field visualization system, the first time ever interactive visualization software for numerical simulations, fully based on the object-oriented technology. BUB spin-off NUMECA is still using his software after more than 20 years. More than 20 BUB PhDs applied CFU in their visualization and data analysis tasks. He is author of more than 70 scientific papers in international reviewed journals and conference proceedings, and in addition, author of several book chapters. He is member of international boards of journals and conferences, acting as chair, session organizer, a reviewer, and editor. He is promoting and encouraging international cooperation in research and development and education, realized initiatives with USA, Canada, Russia, Brazil, India, Egypt, and Japan, among others. He is the European Commission expert in H2020 and member of international organizations AIAA, IEEE, ACM, SAE, and ASME. We are indeed fortunate to have dear professor with us in ICCME 21. I extend a warm welcome to you, sir.
Thank you very much, Dr. Rag. I mean, it was really a very detailed, explanation of my history. I was just passing through all these years, almost 30 years in Belgium, plus 30 years in Belgium, and before also in Croatia, or at that time it was ex-Yugoslavia. But let's start with our presentation, and I'm looking forward to this with very big excitement. So I hope that the audio is good and you can hear me well. So
okay, sir.
Thank you very much, Dr. Rag.
Rag, sir. Yes, sir.
Okay. Yes.
So we can start, and I'm trying to move to the next slide. So you see, it's really a big multidisciplinary project team from the University of Osijek in Croatia, from the DIV design group for naval architecture group, which basically designed this project. And then we have a lot of team members, really multidisciplinary, from mechanical engineering, electrical engineering, architects, and so on, to complete, because the ship is a living object, and all different disciplines have been including in optimizing such design. So here I would like to mention Professor Hederich, who is a leader at University of Osijek of this project, and Mr. Berlic, which is the leader of the team of DIV MES, and all the other assistants are mentioned below. I hope you are hearing me well. I have again to, let's say, just to mention that I am at this moment in Brussels, at the Brussels School of Governments, which is my home university, Vrije University of Brussels, and offers many different programs, which are mostly in the global business, international affairs, European law. So it's more for managers and let's say related to the European Commission programs and the European Commission roles. So it's very good, this school, especially for the people who are operating and trying to find their future jobs in European, let's say, environments and institutions. So here in short, that's already, I was kindly introduced by Professor Rag. He mentioned, let's say, that I went to Brussels in '88, but before that I was studying at Technical University in Rijeka, where I became a naval architect and later a Master of Science in Ship Hydrodynamics, really working on the ship's crew propellers design, which bring me to European programs and aerospace. So I went from the sea to the space and made this interesting CFU program, which is today used in many numerical, let's say, with many numerical solvers. And NUMECA was somehow also my place, because I worked very tightly with Professor Hirsch, who is the president of NUMECA. I'm sorry, this moved a little bit faster. I clicked something, but just to come back, NUMECA software, you will have also today the workshop from Cadence, which is now took over NUMECA, but I think the role of NUMECA in numerical simulations remained the same. So moving from naval architecture, went to Brussels, where I have been also a professor at two different departments of mechanical engineering, and then I also worked on many European projects, more of 20 of them, really especially for the use of scientific visualization. I remember one old project, which somehow 10 years or a little bit more away now, which was working in the same time on the simulation of computer itself, which of course, I mean, in order to do such huge simulation, you need a big computer power. And on the other hand, you need a lot of computer power because you want really to follow different, let's say, scales of physical problems. You go to the microspace of millimeters and milliseconds, and then you go to light years and universe. I mean, and basically all what nature is giving us can be somehow approximated, and we are trying to do that as best as we can. Of course, for that we need a lot of machines, a lot of computers, and normally we need also our brains, because when we compare this computer which we have been simulating, it was simulating a human brain, and somehow when we calculated the energy needed to power this computer, which would be one human brain, would be small thermonuclear plant. So really the energy problem in processing information, I mean, is an important issue, and we want, of course, to minimize it, not only for computer power use, but also for any other means of transportation, like we have in spacecrafts, we have in airplanes, we have in cars, ships. So all the resources we have in nature, we have to reuse in order to have possibility to use it in a very, let's say, perfect way. I would say that we, in the future, we establish a green environment, ecosystem in which we all are going to be healthy and eating good food. Finally, for that, of course, I mean, to operate very well, I need a very good body. So I always done a lot of sports. I was playing tennis, skiing, and golf. Somehow today, just to keep in shape, and that is something which I also pass as a message to all the young scientists, not to forget about their physical, because the good body needs to be to operate a good brain. So let's move further. So my objective in life was always to combine these two things. On one side, you can see an experiment, and then of course we measure some physical quantities on it. And on the other side, you can see the numerical simulation of it. And finally, this numerical simulation is approximation of the nature. And all the time we want basically to validate the both of them. In that way, we are trusting the solution, and we can come to a good engineering designs. So here is the project I was talking to you, I mean, a few years ago, where I was in India, and that was the MAD project, which was also looking to the new way of transportation, an airship. So we had a vertical airship, and if you remember, and the big platform, which was basically a solar energy plant, and all that has to be operating, I mean, in synchronization. So the solar energy was used to power all that, or basically designed to power all of that. And today we will move further to this is just a 3D model. So this is another interesting thing, that we can basically do very precisely our experiments once we design it, and we can scale it up and down and make, let's say, work with it. So this is from Moscow Aviation Institute. At the time I was doing this project. So we have really built up a 3D model in order to test it in the wind tunnel. So this kind of practice, I would really like to advise to everybody. And I think most of the engineers are doing that. So the ship is not going to water if the experiment is not done up front. On the other hand, if you remember, I was also, I mean, working on the heart modeling, so that are medical. So finally, CFD and numerical simulation are not only for industrial products like car, ship, and airplane, but also today become very important for the medical domain. And we are very near that we can digitalize all our body and control, let's say, the treatments, I mean, especially in heart diseases. So a little bit about the fluid structure interaction. So in order to do such, let's say, a modeling simulation, we need to combine different numerical methods. And of course, you know about finite element methods, about fluid mechanics. And also we have the electrical signals, which basically somehow trigger the pulse of the heart. So this is in short let's say, the problems related to this kind of simulation, but we can see that somehow they are transparent to also engineering applications. So what I wanted to say that the medical engineering application are more and more coming tightly together, and we are coming to a real solution, basically combining them. So you can find a lot of information in this book, which I started, so it was, I don't even remember from which year is this, but I was starting about scientific visualization and imaging, which is important in working. And today there is the book from last year on advanced visualization and optimization technique, where I am editor also with Shia Yanarda Khan. She was also, I mean, working with me quite significantly, and still, I mean, contributing to this work on advanced visualization optimization, which we have a conference together. So, to know more about the development of the visualization system, there is a book, and you can find it on the internet just by typing CFU and so on. So here I'm just going to Numeka software now, and you will have today afternoon the workshop on it, where basically this was somehow CFU in all days, but Numeka is, let's say, moving further with let's say, more advanced user interfaces. But at that time, let's say, looking back 30 years ago, that was a CFU system which already showed a very friendly user interaction with numerical data and their analysis. I would like a little bit to speed up this video, so you can basically see different kind of possible representation, different type of quantities, different type of, let's say, information, which is interesting here. For example, for a ship hydrodynamics, you have the wave profile, the free surface, and so on. And then you can play interactively with this data and finding very interesting places where there are, let's say, high pressures and so on and so on. And you have all the possibility of zooming and playing with data. So the numerical simulation really becomes a live object in which you can find the information of interest. So this is about the CFU, and I'm trying to move forward. And normally today, I hope you see the pictures, the Cadence, I mean, it's now, Numeka is also part of Cadence, and of course they have also the fine marine system with many different, let's say, options for shipbuilding. I'm really stressing the shipbuilding because these are the problems we are going to solve in our project. So we have resistance, sea keeping, how the ship is behaving on the waves. Then we have the propulsion element, which are producing thrust, and we have to control it, orient the ship, basically maneuver. And there is also, especially for passenger ships in this case, there is the wind study, and somehow it's related also to what I'm going to show you in the follow-up, because the wind energy is also the thing which we are going to study in our project. So, and the ferret basically is the member of this group, so which is studying and working on the ship, on this very special renewable energy ship, which will be using all the type of renewable energy like solar, wind, and also hydro energy. So a little bit the map of Europe. So I'm here in Belgium at the moment. Osijek is somewhere here with the border between Serbia and Croatia and Hungary. So it's really in the center of Europe. And then you have Split here on the Adriatic coast, where is the Brodo Split, DIV group in Zagreb, my university, also other one in Pula. And now we are going to talk about the real thing of this presentation, and that is the development of the zero-emission passenger sailing ship. Special basic scope of this presentation is electrical part and how to design. So I have to mention that this project is funded by the European Commission, also by the Croatian government funds, and also the Ministry of Economy and Sustainable Development. So all they work together to support this project, and the members of this project is the DIV group, is the shipyard Brodosplit, is DIV the partner for design of the marine and energy solution, then the Faculty of Engineering of Electrical Engineering and Mechanical Engineering in Split, and our, let's say, University of Ferit, which I'm also a member as a visiting professor. So what is really behind this presentation? Behind these presentations is really how to use renewable energy in maritime transport. And we, of course, we would like to be aligned with the nature. We want to sustain the green environment. We want to be, let's say, in the future, I mean, without the now I'm a little blocked, but I will come back, and that how we will go out of these problems which are polluting our environment is really going to be this model ship design, at least for this kind of ship products. So Croatia is really trying to build this emission passenger sailing ship, and we are going then to look to all the elements of this ship and how we are planning to work out. So future developments are going to be also mentioned, because this ship is going really to be built, and already there is started to bring together the material and the elements which are going to produce and in the shipyard build that ship. So there is really a big challenge for us. So it's a zero emission, so environmentally friendly ship. So this is the idea. Why we are doing it, really to sustain, let's say, this European plan of the green continent for 2050, and how we are going to do it. It will be explained in the follow-up slides of these presentations. Who already I mentioned some, and the timeline is about three years, and the expected result, as I already said, is this ship, which has to be, I mean, built in our Split shipyard. So here again, I mean, for your information, this is already, you can see a little idea of this ship, how it looks like. So you can see the sails, and then you can see some wind turbines on it, and also there is underwater, let's say, propeller, which is not going only to be this propeller, but is also going to be a turbine. So, and more information you can get on these already existing website links which are related to the industrial partners and to the academic partners. So for further information, please, I mean, go to this internet link to see more about this. So as I said, the consortium member is the DIV group, which is a project leader of this project. Then we have the marine energy solution, DIV group part, and the shipyard Brodosplit, with the two universities, University of Split and University of Osijek, which are academic partners. So the cost of the project is around 7 million euros. So it's a quite amount of money, but when you are building a ship, I think it's not also so big. So it is going also to be needed, let's say, to sustain this development in the future. So for a new product, I think it's a reasonable amount, but and still, I think there will be a necessity to control this project in full in order to be efficient and make it in the timeline between, you see, it's already 1 year that the project is started, and we will end it in 2023 when the real ship has to be built. So it's 40 months duration project. So there is an experience in the group, and the shipyard, I mean, Brodosplit already built such ships. Here we have, let's say, the small video of Split, so that you can have an idea of the what is the sailing ship about, and also the place where the ship is going to be built. So there are really many elements, and a ship is a complex product because there are passengers, there are crew, and now I am going just to give you a few seconds to relax under this nice music and this sailing environment. So in the background, you can see the city of Split. So this is the final product, the ship, and it's always a great to have it, I mean, sailing. And now the question is how this sailing can be made efficient. There are many different equipments on the ship. So I was just a little bit, I mean, speeding up, so you can see in full the ship which was already built. So it's a great experience in the group to build such ships. And we are coming back to the old, let's say, sailing ships, but really with full of modern technology, let's say, solution to have this renewable source energy in place. And then there is this you can see in the upper right corner, you can see already the design of this new renewable energy, I mean zero emission ship, and you can see already the how we call it, the template ship from which, let's say, this solution came out. So this is already also built. So there is let's say the nice, let's say, jump in technology between the two. And here we have again a small video of this ship which is already built. Yeah. You can note the 3 different sails and some additional, let's say, elements. Really a touristic ship for passengers, I mean, to enjoy, let's say, the sailing, and also, I mean, for touristic purposes. And here there is a new design. Just on the right side, you can also see the underwater, I mean, form of a ship with 2 propulsors, and on the other side, a little bit how we will see it when it will be really built. So all the elements which are going to compose is really regarding to bring new type of propulsion, because there where we are trying to get the best savings in energy. Already that was very well known in the 19th century, and then we went to the steamships and passenger ship, and today we have already solutions with the sails for standard transportation, container ships, and so on. So there is a bunch of different solutions, I mean, following the development, but somehow we are turning back the story and we are going back in history. So there are renewable energy possibilities, and we are considering for that ship, let's say, the 3 main ones. The hydrokinetic, so there is a propeller behind, and I think that is really the big added value to this design, because the propeller is not going only to behave as a propeller, is going also to behave as a hydro turbine. Then we have the wind, which is going, of course, to be used for the sail propulsion. And we have the turbines on the ship, which are going to produce additional energy for the ship services. Of course, on the sails, we could put also the photovoltaic panels, But this maybe for this, let's say, for this moment in this project is not fully considered. We will somehow give, let's say, what the potentially can be expected from such project. So it's really going to be for the, I think that we cannot move immediately eliminate the diesel propulsion, which is already, I mean, somehow a standard propulsion, which is for safety purposes and so on. So we will consider a hybrid propulsion, which is going to be, which use is going to be minimized at most in this, let's say, in the scenarios for sailing and for moving and for powering the ship. So here I now invite Professor Hederich from Ferit, who is really expert in electrical engineering. So I would like to explain you a little bit more about this solution, which is not considered, but I think is going to play an important role in the time to come.
Thank you, Professor Vucinic. Greetings to all. When we, as Professor Vucinic said, when we consider all possible solutions for energy recuperation, we consider different types of already made solution on how to use wind. And as you know, we have on the left side, you see the classical solution with some wind turbine who are grounded on the sea bottom, but then you have problem because you make pollution by building something on the bottom of the sea. You have problem with these towers who need to hold these nacelle and blades of the vertical wind turbines. And also this type of solution have relatively low capacity factor of using all possible energy. In recent time, develop of the drones and as Professor Vucinic says, they already have some study about how to use energy on the high altitude, because on higher altitude from the ground, you have higher wind speed, you have a lower level of traffic and everything. So you can use this energy who are more and more above. And the solution is that connect something on the, shall we say, surface of the sea as a boat to some flying object, and combining the kite, who we know from the childhood days where we played with kites, he pull us out. So wind use kite to move on high speed. It's huge energy, and we, as we see on the study and in literature, we saw the rise of energy can be even 200% above from the normal consideration.
No, it's very interesting that the kite there is flying far away from the ship, because if you would have such a rotating blades on the ship, I think it would be killing half of the passengers. So I think it's it's most appropriate, because we are looking here to a passenger ship, so it needs also to give the good environment for tourism, but obviously it's a big reduction of energy and sorry, a big increase of energy harvesting. No.
Also, this kind of solution can provide a totally new, shall we say, use of this kind of drone and the environment on the bottom, on the passenger ship, because this drone can be during the day some sort of energy source, but during the night or evening can be source of light for the passenger ship.
We wanted to say this kind of solution that we are considering, but it's not going to be the part of the project. Maybe, Željko, sorry for interrupting, maybe we can move to the next slide.
Yes,
I mean, we just show that we are also, I mean, try to understand how it works, but maybe you can give now with this slide a little bit more, let's say, elements of how it is, the energy is generated.
Yes. So basically, wind blow the kite, and kite goes farther from the ship, pulling the rope, this connection cable. So on ship level, you have a generator who is, shall we say, turbined by this dragging connection cable. And when the kite go further on the, shall we say, a long distance, then you can turn it to go flying back to the zero position. And in these two phases, you have energy production and energy recuperation. and when kites go back, you don't use energy. So basically, you have impulse of energy in several occasions and benefit to the energy in the ship, because you have energy on sails, but on this level you have multiplied this energy by speed up of the wind speed.
As we are not really considering it in this project, I mean, we are going maybe to consider for the future potential projects, and basically if there are interests between the audience and that in this kind of solution, we would like to establish a relationship, maybe to build a next proposal for such, let's say, propulsive power.
We must say that this is not our solution. This is already established a solution from several research groups we find over the world. So a huge number of researchers already looking for this, and we try to be part of this.
But not maybe for the passenger ship. That's what I
mean.
But here there are, let's say, some new, let's say, models. Željko, as you mentioned, we are looking to let's say to different state-of-the-art solution, and here we have basically a very special yacht, which is Black Pearl, and we are considering the data they are providing, but this is they are reducing really the fossil fuel consumption and recuperation of wind energy, but it's also not a full, let's say, system like we are considering in our design. But we wanted just to mention it as a state of art, and here there is still not a build yacht, but it's done on solar panels, and the sails are used as a solar energy plant to, I mean, generate electrical energy. So, as we already, I think you are fully. I'm sorry, somebody has the micro open and we are having some noise. So maybe I would like to ask the audience to close to switch off the micro. Yes. Okay. Thank you. So the objectives and expected result of this Equinox 3 passenger ship is already, we mentioned different propulsion, let's say, solutions, and it will be an environmentally friendly electric ship, and it will be sustainable with zero gas emission. So in order to, I'm sorry, I was clicking something too fast. So in order basically to get to such, to solve this and to reach these objectives, this, let's say, consortia is quite interesting, because it's bringing together the technology, advanced technologies which are researched at the university, and also then, I mean, integrated by industry in this new cruise ship product for tourism, which obviously for Croatia will be really a nice product for I mean, for whole the world. And I hope that this is really going to be the future of shipbuilding in Croatia. So how basically to come to this and how to develop that? First it was done the ship design and related technological analysis, already mentioned, of the current state of art for this kind of propulsion system and forms, and then there is also a big aspect on the interior, because the ship has to have many I mean attractive solution, especially for tourism. And how you do it? First, of course, you start with the ship hull, and you have to do a lot of simulation and also the test in the model basin. So this has to be to make, especially here for the sailing passenger ship, the sails are of important element which has to be controlled and developed. So all this hybrid propulsion and regenerative electric drive has to be integrated with the parameters coming from the hydrodynamic simulation. So as already said, the sails are there, and they can be better than conventional sails. So we can also consider different new technology to have these sails, I mean, developed, and they also call fixed sails. So they have really a fixed profiles with all the new materials coming in there, let's say, how they are constructed and so on. So the power production for batteries, electric is, let's say, the sources are the hydro turbine, the solar panel, and the wind turbine. So these are going to be the three main sources on this ship. And we will be also designing the control system, which we will see a little bit more in the follow-up of this presentation, which are going somehow to control the electrical system of the ship, the production and distribution for different, let's say, for different purpose. So the ship prototype will be constructed. There will be sea trials. So we will have a real ship from which we will get much more information of all and feedback on the, let's say, on this idea which we have put forward. So here, basically, again, a short video to show you, let's say, how really the ship design process is going on. Of course, you are first designing it from the on table and in the design offices, but then all that comes to the shipyard, and in the shipyard normally it's built, and you put it on the and then the ship hull goes to sea, and all the equipment later on is going in the ship. So this becomes a process, which all this process will be done, and you are really looking to the Brodosplit shipyard in which this ship is going to be built. So it's always a very exciting moment where the ships go to water. I mean, and of course now it has to be deported to the harbor where it will going. The other equipment will be further, I mean, bring in the ship. So this is a little bit from design to the real ship, and this project is all about that. So here, as you have just a visual of this new ship with some more attractive, let's say, viewpoints. I mean, you can of course see the sails and the wind energy. Okay, here the underwater shell form, but here there are the line plan of the ship. So this is going to define the hydrodynamic behavior of the ship. And we will do, let's say, this modeling to find out, let's say, the optimal, let's say, form for this product. So normally the ship design starts with understanding the volumes of the ship. Here is just an example of the passenger ship, and you can see different, let's say, the engine room, the control room. So all that has also to be integrated in the sailing ship design. And now we have it already here.
May I please interrupt? So we have 2 questions in the chat box. Would that be fine if I read the question right now?
Sorry, can you repeat a little bit louder?
So we have 2 questions in the chat box.
Yes, please.
May I please read the questions right now?
Yes, yes, yeah, you can.
Yeah, so we have the first question. Can we consider the solar panels as really renewable energy, since the disposal is always a serious concern?
I did not understand a little bit the last part of the question.
I repeat, sir. I repeat. Can we consider solar panels as really renewable energy, since the disposal is always a serious concern?
Yeah. This is a very, very good question. Yeah. I mean, in the complete value chain of this solution, of course, this is a problem. I don't have an answer to that.
If I may say something, that practically today we don't have any renewable sources. They are fully, shall we say, renewable. The problem is production, who are mainly designed on the level of old industries, who are still using a lot of steel, a lot of that thing that can be replaced and, shall we say, recycled. But new technologies have problem. Battery, photovoltaics, even thermal have problem with this. This is something that new research have to dismantle and to understand how to dispose of this energy. But we now think that renewable energy sources are basically those who can use the sun, wind as a source. The problem of what later will be later is concerned, but it's in progress. Solar app today is not a good solution because have a very low level of energy efficiency, but progress is practically every day.
Maybe, Željko, we can just mention that for Clara, I mean, the solar panels are not going really to be placed on the sails, so it will be really a limited use of solar panel just for hot water generation.
We will probably mostly use thermal photo panel, so we will use thermal energy, not photovoltaic, because we have so huge implementation of hydrokinetic energy that we don't need the solar in this project.
Yes,
so there will be no photovoltaic in this project.
But obviously we have to consider it because I mean all the new design going this direction, so we have to address all the points which we
yes
can.
Energy from the sun is big, and we have
but
to
I think
consider
we have this. I think we quite well. I mean, thank you, Željko, for answering in full this question. Maybe the second question, I understood there are two.
Yes, we have one more question from the participant. Destructive tests are unavoidable in some situations in automobile industry, especially in car manufacturing. What will be the counterpart of such situations in shipbuilding? How is it dealt with?
Well, in shipbuilding, we don't do this. We do previously a lot of, shall we say, numerical calculations, etc. Nobody crash the ship for some damage. It's too expensive up to date. But on the small scale model, do.
We know that there is always the experimental, let's say, simulation, or let's say the experimental measurement require bigger investment than numerical simulation, and that is really all the, let's say, game going around. I mean, to optimize, let's say, the experiments to minimum. But here we will have a real experiment. I think this is a big value for the feedback. Any other question?
So we have one more question. Is there any possibility to utilize energy flow induced vibration to power the ship? Is there any possibility to utilize energy flow induced vibration to power the ship?
Yeah, this is a good question. For the moment we did not found, let's say, the appropriate application for that, but I know about that work, and we will surely consider it. So it's basically when we would have an oscillating wave, let's say, like I was showing this with the bow, the experiment jumping the bow in the water. If the bow would be oscillating, I mean, it would create also electrical energy. So like extraction energy from waves. I understood. I think that is the concept which can be, let's say, used as renewable energy. Yeah.
If I may answer this question about...
We did not consider it in this project.
Yes, there are many renewable sources, but if we use part of this not as hybrid solution, then it's not efficient. But we use hybrid solution, so we use what energy is available in some moment. So I think
we have to progress with the
same thing I just said.
We are now on the different, let's say, just a little bit breaking down the ship in different levels, decks, how they call it. So this is the bottom one, and maybe I could ask the assistant from Professor Hederić.
Kolega Čačić.
Yeah, Mario.
Thank you, Professor. Nice greetings to everyone. So these are ground plans for the template ship called Clara. So here on the presentation we can see a lower deck and some photos. Here is the main deck, and it's also quite a luxurious ship. So here we can see the ground plan and photos of upper deck. And based on this template ship was built our new zero emission ship. So you can see here the plan for this ship. So there is also ground plan for bottom deck, and here we made some areas so you can see propulsion, battery space. Here is the freshwater store. Also black water tanks marked in green, and warm water tanks. So here is the ground plan for lower deck with passenger cabins with average cabin size around approximately 35 square meter, crew cabins and crew mess and laundry.
So the ship is a big living space for many. I mean, for the one who are serving the ship and for the ones who are enjoying the ship. So
yes,
all spaces has to be well designed.
The crew, there is a crew of 12 members, and this is the galley space of 60 square meters and engine room. And
sorry, I went too fast.
Here is the main deck, the space for there is the open saloon and deck bar, and also clothes saloon and some other passenger cabins.
And then finally we are moving to the sails and to the solar panels, which are on the captain bridge and so on. So thank you, Mario. I mean, for, let's say, giving us a view on this deck breakdown, and of course, as you could by now, you obviously know there are wind, hydro, and solar energy. I mean, sources on the ship. The product is environmentally friendly, and the aim, as we said, is to reduce the noise pollution and gas emissions. So here there is now we have even the name of this new green sailing ship, which is called LEDA, and here are the, let's say, the elements of it. Of course, I mean, to simulate all that, we need, because as we had this question, I mean, between, let's say, the experiment and the numerical simulation, I think we need a good tools. I mean, to simulate all the hydrodynamics, which is related, especially for the hydro energy extraction from the water, because as already mentioned, the big advancement in this technology for this project is that the sails are going to produce the thrust of the ship, and the hydro turbine, which is basically the propeller, which is just going to operate in the different way, is going to bring back energy, mechanical energy to the generator, and is going to produce electrical energy. So all that has to be somehow simulated, and we really have to understand in detail how the ship flow goes around the propeller. And for that, we have then the CFD software, which can help us with all these parameters. So here we have just a standard ship with standard diagrams. Here are the two softwares. One is Fluent, one is Flow Vision, which is calculating this thing. And obviously each of them can do more or less the similar things. And but finally we have to get as a result these diagrams. And of course, then we have also to look to the sails, because the sails have also influencing the behavior of the ship. And then we have, I mean, to consider this input, which then we will then have our ship form we are going to put in the model, and we are going to make the computation. So this is a standard process of numerical simulation, just a little rehearsal on that, making the computational domain, understanding the center of masses of the ship in order to be in the possibility to calculate the movements on the waves and so on and so on. Okay. This is just to give you an idea. Then we get what is the output of that is the resistance and the lift, and finally we get the motion out. And here, please have a look to this nice, I mean, simulation from the code Basilisk from France, which we show the sailing ship, and I think it's nice to see how this is behaving. And so this water, this stream of water is coming to our, let's say, propeller, which is a generator, and then we have all the, let's say, the hydrodynamic data for our new ship. from the sister, and here are some of the main elements, and this is now the model which is going to be built. And now here we have so the model is designed by the DIV group. The let's say sails, solar panels, and wind turbines are designed by the University of Split. And then the ferrite elements here, and maybe Željko, I need now a little bit your help here to explain, let's say, the role of the ferrite university in this project.
Yes, thank you, Professor. We have to say that we have a university from Split who are very good in this project and have a lot of, shall we say, assignments. So they are on the sea level. They are close concerned with the shipyard, and they are much more, shall we say, professionally related to the ship building. So sails, even the dynamics of the ship. The electrical faculty from Osijek are more concerned about automatization, optimization of energy flows, etc., in the ship. So our concern is energy flow in the ship. So you can see here that from a battery as a storage of energy, we need to give a flow of energy from the sails, from the generators, from the wind generators, from the photovoltaics. All this energy come to battery, and from battery go to the propulsion motor. Propulsion motor in some times when it's optimal become generator, also practically turbine. So the screw of the ship is propulsion and then turbine. And this, shall we say, double role of these three parts give us energy flow.
So
but
this is really a very complex system, and of course
yes,
there are many elements, but because I think
it's very complex to combine. That's why we develop a simulator for that, and not just simulator on the computer. We try to make simulation on the real motors, and we will make the measurement on the real ship, get parameters, then this parameter will be, so please next slide, this parameter will be used for making simulator, and this simulator must provide the shall we say, space of the possible solution for future captain when he control the boat on some, I don't know, windy situation, no wind, yes wind, or maybe in the have more sun. So this simulator will provide a lot of data for the future, shall we say, control of the ship. So this data, Professor Vucin is mentioned on the beginning that you need a lot of computational energy and a lot of computation time to calculate this. Captain of the ship doesn't have this time. We need to provide the data before he is on the some, shall we say, situation, so that he can get easily this energy. So after this simulation, we make this in computer simulation. We're using MATLAB as, shall we say, academic tools. So please, next slide. Yes, so you can see that this simulation provided a situation when you have used electric motor as propulsion, the red, shall we say, lines and a red situation. But in some situation when you have good wind, etc., this motor become generator, and this green area present energy you can get put back to the battery, changing the shall we say, mode of the machine. This machine, the propeller and the machine become in one situation propulsion, in next situation become hydrokinetic turbine. And shall we say, captain says, I want some, shall we say, driving cycles, I want to speed up or speed down, and demand of this demand of the speed, we calculate how much energy we can put out of the battery or put back to the battery. And as you can see, we have several, next slide please, Professor, several energy storage. So from propulsion, regenerative braking, from wind, these two, shall we say, horizontal wind turbine, and from solar. So you can see that the ratio between this energy are more in the scope of electric propulsion, and that's why we don't talk too much about this. But
so we are really looking to this hydro electric, let's say, regenerative source, because the other ones are really small in our design.
Yes, but next slide, please, Professor.
Yes.
We consider that as, shall we say, research. What will be if we use this, shall we say, photovoltaics on the sails, on the ship, shall we say, surfaces, or maybe using this additional kites, or I don't know, drones.
Yeah,
so
but
this is
it obviously, I mean, we could double the energy. We could go from 300 there to 600
That's
there.
right.
No?
But
Yeah.
this is something that should be considered. But we have to build something that is real, that can be made in the reasonable time of 42 months, and that can flow. And this is why the deep groups make solution that it go only on this level of solution with hydrokinetic energy.
Yeah,
In future,
so
we will
this
demand
really
everything.
electrical system has really to work on this renewable energy propulsion. Really, hydro propulsion is the source of electrical, let's say, support for ship operation and passenger facility. So it's really coming mainly from that source.
Yes, but as you said, Professor, the ship register is something to propose that you have to have, shall we say, redundant energy sources. So you need to consider everything.
Yeah, and especially for safety of the ship and so on. Yeah. And here we have really how, let's say, this the hybrid engine room is really something special of equipment which will be done in this ship. And here you can see a little bit how maybe we could ask Juraj to give us a small, let's say, description of this video.
Hello, everybody. Yes, so here we can see engine room. We can see a lot of equipment. Most of these are maybe some fans, some battery equipment for the equipment of the propulsion motor or for load flow. This is some hybrid engine room in the ship. As you can see, this is a big room. It's very heavy equipment, and it's taking a lot of space. This is the problem with battery, because 1 kilowatt hour corresponds to 10 kilograms of weight. So here are some pumps, some fans. Yeah, in engine room, it's very noisy because all this equipment is working at the same time. So some pipes here.
Sorry, Juraj, for speeding up, because I think our time of presentation is a little bit going out, but I think this is going really to be the innovative element of our ship. I mean, already,
yes,
of course,
here are solar panels. As you can see, solar panels on the top of the ship.
Mm-hmm.
But this ship is, I would say, this is some bulk carrier. So this is a much bigger ship than our sailboat.
And has different let's say, requirements for design. So let's say we will,
and more space than our ship.
So
yes.
Let's go to the conclusions, because we use all our time. So thank you, Juraj. And so I hope we show you in short the progress in the zero emission passenger ship sailing project, which is undergoing in Croatia. And we are very excited that we could basically show you this, let's say, present you this project, so which is the renewable energy solution for propulsion, especially hydro propulsion. And we hope that this prototype ship will be really a big base for the near future product of these types, especially for ship, for sailing ship for tourism. And of course, it's an environmentally friendly product for the Green Europe, challenge, which is established for 2050. And we really look forward to make it done. And And I say I'm personally very much excited. And I mean, this team, I would like just once more to congratulate Professor Hederich. I mean, to be part of that, because he is also a very interesting, let's say, have ideas for rivers and for there are small, let's say, small scale solutions which he is considering, and I'm really looking forward to, I mean, for this type of new projects to come up. Then we have a big team of DIV, which basically bring together all the and made the ship. So it's really, I think we have a multidisciplinary team which has all the elements to be successful. So, and I thank them all for this contribution. Of course, before closing this presentation, I would really thank all the members who contributed to presenting this. So it's a very university from Osijek, and the members today which have taken place in this presentation, then the members of the DIV group which are in Zagreb, then the flow vision software from Capvidia, I mean the marine software from Numeka and Candence, and my Brussels School of Government. So I thank them all for giving us possibility to show their material too. And of course, before fully closing this talk, I would like really to give my special thanks to Dr. Vijay Chandra for the invitation and for organizing. And it's really an exceptional moment that we could basically present. That it really is a project we started, and it's really a great to think how that will be ending. So also to the big patron and the chairman of the SCMS group, which I mean, Dr. Nair, and then the patrons, Professor Pramod, and which I met on several occasions, and I really, Professor Gopakumar and Pravensal, I really would like to thank for making this event possible, and really big thanks to all the organizers. So before closing, I mean, there is a question, there is my email here, but of course, I mean, it will be passed to all the groups, and you can have basically replies on all the questions you have. So once more, thank you for your attention, and thanks for, I mean, making me part of this nice event. So looking forward to continue interacting with all of you. Thank you.
Thank you, sir. I invite Dr. Vidya Chandran, Organizing Chair, ICCME 2021, and the Associate Professor, Department of Mechanical Engineering, SCMS School of Engineering and Technology, to propose a word of thanks.
Thank you, Sanju sir. Let me do my duty. Dear Professor Dean, it is indeed a privilege to have you with us here for ICCME 21 and to continue our association since 2015. I remember Dr. Shija, our former HOD, head of the department. She was really excited to find Professor Dean and explained to us that the person standing in front of us is none other than the creator of the codes of software which she had used for her PhD research. And since then, we are closely associated with Professor Dean, and we were also lucky to have him here at our campus during two important events. I take this opportunity to sincerely thank Professor Dean for readily accepting our invitation and joining us to enlighten the participants on this very important and promising project. I thank Professor Hedrich, Professor Mario, and the project consortium for joining us too. I express my gratitude to the project consortium, which consists of DIV Group, Marine and Energy Solutions DIV Limited, Brodo Split, member of DIV Group, University of Split, Faculty of Electrical Engineering, Mechanical Engineering and Naval Architecture, University of Osijek, Faculty of Electrical Engineering, Computer Science and Information Technology, for being with us on this very special day, and for throwing light on the new project and about the ship Clara. Once again, I thank Professor Dean for this very lively session and hope to meet him on the campus for a post-pandemic conference. Thank you, Professor. Thank you so much for joining us.
No, thank you very much. I mean, it was a big pleasure and privilege, and I will continue to serve as best as I can. Thank you.
Thank you, sir.
As all
Over to
good
you.
things must come to an end.
Thank you
Tomorrow-
for hosting and greetings.
Yeah. Tomorrow we have the keynotes 3-4, technical sessions 3-4, and the Numeka workshop. All participants are requested to be online at 9 a.m. tomorrow. It's time for me to announce the end of the first day of International Conference on Computing in Mechanical Engineering 2021 with a virtual tour of our campus and the God's own country, Kerala. See you tomorrow. Until then, goodbye and thank you.
Thank you, everybody, and looking forward to interact.
So please stay for our virtual tour. We welcome you. We welcome you to a virtual tour to our Kerala.
Thank you.
മുത്താളം മുടിതാളം കളിയാടും നാടേ നിൻ തുഞ്ചത്ത് മുത്തോളം മുകിലോളം മലയാളം പാടും നിൻ തീരത്ത് പൂപ്പൊലിപ്പാട്ടീണം മൈലാഞ്ചി പാട്ടിനഴകൊടു കൂട്ടുകൂടും നേരം നല്ലോണം നമ്മൾ കോണം മിന്നൽ പൂരം തുടിതാളം മഴയുടെ മേളം നീണ്ടു നിൽക്കും നറവനതാളം പരിചകളുടെ വേരൊളി മേളം നെഞ്ചിനു താളം നിലവിനു മേളം ഇടക്കയുടുക്കുമുടുക്കുമിളയിടം
Thank you all. Thank you. See you tomorrow. Goodbye and thank you.